decades. So basically, you can see that starting from the middle of the previous century, every next decade is warmer than the previous one. And basically, the gap is also increasing a little bit. Then on your left, or right-hand side, there's the years with the higher record high temperatures over the history of observations. So basically, what we can see here is that the warmest years on record all happened in the 21st century, and basically the last 8 years are the warmest, basically. So the warmest as of today was the year 2016. But this year, 2023, has all the chances to actually be even higher. This is the graph demonstrating where the temperature so far is. And so basically, we are kind of, after 9 months, the year 2023 is third in record in terms of warmth, but since the temperature is now really higher than all the previous temperatures on record, then probably by the end of the year we will see that, well, this one is the most warm. Oops, sorry. Let's make it back. I have a few nice pictures that actually demonstrate the departure of temperatures from the average of the last century, like on a year by year and actually month by month. So you can see that when it's blue or white, then its temperature is below the average, and if it's like red or purple, then it's higher than the average. So you can see that it's not by chance, basically. So the temperature is actually increasing all over the period. Let's see what's happening next. This is another one, which demonstrate more or less the same, but in like you will see here that the southern part is warming a little bit quicker than the northern part of the planet. And the warmest regions or areas on the globe are those the poles, especially North Pole, but also the South Pole as well. So Antarctics as Arctics are both warming very, very rapidly. Now another one, which actually demonstrates the temperature over the land and over the ocean. Again, it's like 5-year average, to avoid, all these fluctuations, which are more or less stochastic. So we make it like five-year period average. And again, you can see that over the time period, the temperature is actually rising. And in the Arctics, it's kind of like astonishing, right? So and the parts that are covered mostly by this high temperatures pattern are European part and Russian Siberia and China, basically, especially, right? Now the driving force behind this temperature rise basically is the increase of the concentration of CO2 and other greenhouse gases, not only CO2, but mostly CO2. And here's the graph on your left demonstrating the concentration of CO2 over the more or less 800,000 years. It was more or less stable. I mean, in the way that in nature something can be actually stable, like circulating, but more or less over the stable average, something like 270 to 180 ppm, particle parts per million. And now all of a sudden it's like 400 ppm. And basically this last big rise was caused by the human activity. So on your left side, you can see the same graph, but only for the 2000-year period, like from the birth of Christ, more or less. And so it was really stable over this period of time. And then all of a sudden, within the last 150 or more or less, this period time is increased drastically. In terms of CO2, it's more than 50%. If you look at another greenhouse gas like methane, then it's actually 2.5 times higher than it used to be over the period. Now, to what extent it does matter, basically. So we know this very well known effect, which is called greenhouse effect, which actually means that there is something in the atmosphere that prevent the heat from escaping into space. And basically, the first guy who opened this effect was Jean-Baptiste Fourier. It happened back in 1827, basically. So it's like 2 centuries ago. We already know that there is something in the atmosphere that actually provided additional heat to the surface of the Earth, and this is something which is now we call greenhouse gases. The first one that was actually identified as greenhouse gas was actually the water vapor, but the water vapor doesn't live long in the atmosphere, only for 10 days maximum. Then it actually crashes down on Earth. And there are some other gases which actually stay for years and even for centuries. And one of those long-lived greenhouse gases is actually carbon dioxide, or CO2. And actually, it can stay in the atmosphere for a millennium. So that's why, and what it does actually, they do not prevent the energy from sun to go down to Earth, but then they prevent the infrared radiation from escaping into Earth. So they trap it and then re-emit it back into the Earth several times. So basically, it's not due to human being activities. It was for a long time already present in the atmosphere. And if we calculate more or less the impact of greenhouse gases onto the temperature, then it will be probably something like 30, 33 degrees centigrade. So without greenhouse gases in the atmosphere, the average temperature on the planet Earth would be negative, something like -20. But because of the greenhouse gases in presence in the atmosphere, we will have like more or less around 14 degrees centigrade above zero. Now, but the trick is that when the concentration of greenhouse gases in the atmosphere increase, then the amount of heat which is actually reaching the surface of Earth increasing as well, instead of escaping into the atmosphere. So basically, what we see on your right is more or less that what we actually observe so far. We have the increase in the concentration of CO2, and we have the increase of the temperature, the average Earth temperature over the same period of time. Are there any other factors that actually can change climate patterns on the planet Earth? Yes, they are. I would not speak more about like geological. They're very well known. If we look into the Milankovitch cycles, then it's all about the shape of the Earth's orbit around the sun. Then it's like some other factors, but they are actually changing very, very slowly. So it took like hundreds of thousands of years for those changes to happen. But if we look into something that actually changing within the period of time we are interested in, something like hundreds of years or centuries, then the first one we would look at would be the activity of the sun itself. And we can see on this graph that over the period that we are looking at, like more or less 150 years, then it was more or less stable. So we have fluctuations, but they are around more or less the same, right? So it's close to zero. Then another one is the volcanoes, but when the volcanoes erupts, then we don't have climate changing into the to the warmer, but on the contrary, when the volcanoes erupts, then actually they emit a lot of aerosols into the atmosphere, and aerosols actually they reflect the sun energy, preventing them to reach the surface of the Earth. So basically, when you have eruptions, then basically you have the cooling period, the cool period on the Earth. Another one which we actually emit when we burn coal or some other fossil fuels, actually we also emit aerosols in the atmosphere, but they're also cooling. So basically, the only one factor that actually drives the climate to the warmer side is basically the emissions of greenhouse gases, and particularly CO2. So on your left side, you see like looking backward, and on your left side, you can see the same looking forward. So basically, if we would continue emitting CO2 and other greenhouse gases the way we do today, so basically by the end of the century, the temperature will be 3 degrees centigrade higher than in the pre-industrial level. So far, we have something like 1 plus 1, something like 1.1 degrees centigrade higher than it was in the pre-industrial period, but it's going to be 3 degrees centigrade high by the end of the century if we go on like we used to do previously. Again, this is very, I would say, the graph that says for itself. Basically, it's the concentration of the CO2, which is the blue line, and then the gray line or the black line is the amount of CO2 actually we emit on annual basis. And you can see in the year 2020 something happened, and you I guess know very well what actually happened. It was pandemic, right? So due to pandemic, all the transportation was kind of stuck. So we didn't fly, we didn't drive, we sit at home more or less. So that caused the emissions go down a little bit, more or less something like 7 or 8% maximum. But still we were emitting. That's why the concentration still were growing up rather than, going down or being stable. And I once again would like to mention that the temperature actually is the function of the concentration rather than a function of the emissions, basically, right? So do not confuse, because some people would tend to ask, well, if the emissions went down, why didn't the temperature went down as well? So it couldn't. We are still emitting, and that's why the concentration is still growing, and that's why the temperature is still growing on average. But we also have something on the planet Earth that actually remove the CO2 from the atmosphere, and we have like two big stocks which does that. The first one is ocean, and the second one is actually forests and wetlands. They're both like kind of absorbing or sucking down the CO2 from the atmosphere. So some part of what we are actually emitting in terms of CO2 are now absorbed by the Earth, I mean ocean and land, but not all. They cannot actually compensate with the activity all the emissions that we actually produce on annual basis. So something is still left and stay in the atmosphere and increase the overall concentration. Okay, I can again demonstrate this stuff. Oops. Yeah. So basically, you see the human-induced CO2 emissions into the atmosphere, like big arrows, and then the smaller ones, it's two streams from down from up to from bottom from the atmosphere down to Earth, but they still cannot absorb everything. So the figure behind them is still increasing. It is the figure behind them, painted in red. This is actually the concentration left in the atmosphere. So far we were still increasing the concentration, so we're still producing the prerequisites for the temperature to go up further. Because we do so, right, and because we like increasing the amount of infrared or heat basically reaching the surface of Earth, then the question would be where it goes. So most of the additional heat that comes to Earth from the atmosphere goes into the ocean, something like 90%. A little bit goes into melting of ices. I mean, the ices in the ocean, on land, and basically in the mountains. And something is still left to heat a little bit the atmosphere close to the surface of the Earth. And the bad news is that the amount of heat reaching the Earth actually is increasing over time. So it used to be something like 0.5 watts per square meter, and now it's 0.8 watt per square meter annually. So it's kind of a, like astonishing thing. So it means that actually we have the imbalance That's why the temperature is actually rising, because if we would have the stable situation, then the temperature would not be rising, right? So we will be emitting back into the space more or less the same as we receive, but it's not the case so far. That's why we would be still increasing the concentration, and we will still increasing the temperature, and so the climate would be going warmer and warmer. So basically, the term, this language, which is called climate warming, means that not like it's by itself, right? It is because we are doing something with this climate. We are warming the climate. So the initial meaning of that word, that it's not by itself, but it's like a result of the activity of the humans on the planet Earth. Well, where do we stand now? So far, as we can see, based on the recent report by the IPCC, International Intergovernmental Panel for Climate Change, so they actually calculated that so far the overall average temperature on Earth is 1.1 degree higher than in the pre-industrial level. Of this increase, the human-induced increase would be something like 107. So, but if we take the last 50 to 70 years, then probably the all increase of the temperature in the atmosphere is actually human-induced. So, right, over the 150 years, it's the dominant part. But if we only limit ourselves to the last 50 to 70 years, then it's like 100% increase is produced by the humans. So the previous year, the year 2022, we have actually the report by the World Meteorological Organization. They said that the departure from the pre-industrial level of the temperature was 1.15 already. So if the things would go on like they are now, so by the end of the century, we will have completely different climate on the planet Earth and completely different biodiversity, because most species cannot survive into the new climate and will certainly be degraded. Now, the worst scenarios are here, so like kind of catastrophic scenario. There is kind of 10% probability that by the end of the century, the temperature would rise more than 6 degrees centigrade from the pre-industrial level. And that would be the disaster, basically. Yes. And this is the same in terms of the water level and the oxidation of the water. You can probably guess very easily why the sea level is actually rising. There are two factors for that. Actually, heating itself, more heat water actually tend to have bigger volume. And another one is melting of ices and the mountains and on the land, especially Greenland and Antarctica, are adding a lot into the sea level. And by the end of the century, the sea level will be 1 meter higher than it used to be. And it will not stop there. So during the coming 2 to 300 years, it will be even higher. And oxidation, because the CO2 is actually absorbing CO2 from the atmosphere, its chemical content is actually also changing. So the water becomes not only warmer, but more, how to put it best, acid, so to say, right? And for many species living in the ocean, this is not good news at all, right? Now, the disasters, which are the acts of God, so to say, which actually brings million or more damages. This is the picture that, demonstrating what happens in the US, but basically around the globe, we have more or less the same picture. Back in 80s of the previous century, we had more or less one big disaster within 3 months, like 82 days. And now we have one big disaster every 18 days, basically less than 3 weeks. So this is the difference. We don't have actually time to mobilize resources and to deal with those disasters, not only because the population is bigger, not only because we have the economy higher, but also because those disasters are happening more frequently and they are more intense than they used to be. not quite sure that we are in time. Let's see that apart from that, we will also have some rather negative or adverse impacts of climate change on mortality and health. So this graph demonstrates what particularly is happening, especially for the elder people, which are suffering from the heat waves and other like negative effects of the climate change. We also have the problems with the international, regional, and national securities because of the conflicts arising from the scarcity of fresh water, but also agricultural products like food, and especially in the southern parts of the earth. I mean, not southern, not quite correct. It's actually tropics rather than southern part, right? It's something like Middle East or northern part of Africa. They are really suffering from high temperatures and agricultural problems. Like droughts, there's not enough precipitation, so they have problems with the crops growing, and so there's a lot of starvation and the lack of water. We actually observe it right now already. It's like a popular book, not the scientific one, but it appeared to be really popular, and it is called The Uninhabitable Earth. Life after global warming, which says that basically if we go on like this, then in certain parts of the planet the conditions would be not even uncomfortable, but they would not allow actually the human to live there. So that's why in some parts of the world the planet would be became uninhabitable, not only in terms of humans but also other species as well. A little bit in terms of economic damage. So it says that if the temperature would grow up to 3 degrees centigrade by the end of the century, so we would be wasting something like 18% of our global GDP if we stick to what we think like more or less safe, or what we can actually still reach in terms of Paris Agreement. Then we will be losing something like 4% of GDP annually, which still means a little bit of losses, and the distributions between the countries would be very high. So the countries, the weak countries, so the countries, least developed countries, they will be losing even more, something like 10 or 12% still. And the countries to the north, like America or Russia, they will be still losing, but much less. So in many parts of the world, we can now see this new trend, which is called climate emergency. So a lot of municipalities or national governments declare that the climate situation in the region is kind of the like emergency. And this phrase or this terminology was once used by the UN Secretary General Antonio Guterres, who actually called the global climate situation as climate emergency. So basically it means that while maybe not the biggest problem in those regions, but one of them at least. So something has to be done really quickly in order to improve and in order to escape the worst consequences of the climate change in those regions. Do we have any instruments in place to deal with climate change crisis? Yes, we do. Today we have this document which is called Paris Agreement, that was adopted back in 2015. But basically this is the third one. The first one was adopted back in 1992, and it was called UNFCCC, United Nations Framework Convention on Climate Change. Then there was the second one adopted back in 1997, which was called the Kyoto Protocol. And now we have the third one, which actually starts practically in the year 2021, when the second period of Kyoto was over. It was over back in 2020. So starting from the year 2021, we're living under this Paris Agreement umbrella, so to say. So the targets of this document basically are, in terms of climate, to hold the increase of the temperature well below 2 degrees centigrade. Well below it, it's very diplomatic. I don't know what exactly that means. But at the same time, the target also anticipates that everything would be done to still hold the increase within 1.5 degrees centigrade above the pre-industrial levels. This is the wording of the agreement, but basically, if you consider the narratives in the bigger politics, then basically it's like vice versa. So 1.5 is normally mentioned first. So we need to do whatever we can to limit the increase of the temperature within 1.5. But if for whatever reasons we fail, then we should at any means, prevent the temperature to rise even close to 2 degrees centigrade, right? So this is how it interpreted in the real life, instead of in contradiction to what is actually said in the agreement. So the narrative kind of changing over time. And there was a reason for that, because in the year 2018, IPCC actually released the report, which was called 1.5 degrees centigrade temperature rise, and actually it was all about the difference between 1.5 and 2 degrees centigrade temperature rise, and it says basically that there is big difference. So starting from that time, the language actually of the climate politics changed, and 1.5 is now mentioned first, and then as plan B. Right? If we for whatever reason, if you fail, then no way it should grow close to 2 degrees. But actually, the climate target is not the only one. So basically, in the same clause of the document, there are also two more targets. One, which I would call like economic, and sometimes people tend to say that it's all about adaptation to the climate change, but basically it's not. It's also about the mitigation. So we can do something actually to prevent the temperature from rising. So, and what we can do, and we should do actually, is to switch to the low carbon development model, or low carbon development route, so to say. And here in the document, it is called low greenhouse gas emissions development. Sometimes people kind of lose this narrative, and I, at least like last week or something, I came across a brochure published in Russia, and all of a sudden this greenhouse gas low greenhouse gas emissions development was like forgotten. So they only focused on adaptation and resilience to climate change, but not on mitigation side, which is, of course, a big mistake. So basically, the idea would be that in order to prevent the climate from changing further, we have to actually to improve our economic activity and to switch to low carbon route instead of high carbon route that we are experiencing now. But there's also the third target, which is about finance. So the second about economics and the third about finance. And the idea that we can actually rebuild the money flow in the economy in such a way that actually those money should be used to help the planet to switch to this low carbon and climate resilient route, right? Instead of what we're doing now. A few years ago, there was a calculation made by Mark Carney, who at that time was the governor of the Bank of England, and he was by the time also the chairman of the Finance Stability Committee of G20. And he calculated together with his colleagues that the investments made by the financial system is leading the world by the trajectory, which actually means 4 degrees centigrade increase by the end of the century. So the investments already made are made incorrectly, and we have to do something very rapidly with that and change the way that financial sector treats the risks. And since that time, we're now facing, and the new concept was introduced, like climate change risks, and financial system now has to keep in mind that there are consequences of particular investments, and those consequences should be taken into account. Now, another clarification put into the agreement is that by the end of the century we should balance our emissions with the removals from the atmosphere. So meaning that by the end of the century we should emit like net zero, more or less, right? And maybe you heard this terminology, net zero, meaning that whatever we emit, so something that actually we absorb through the forests or wetlands or whatever, should be more or less the same. But basically it should be even higher, because we need to reverse the trend. Instead of keeping the concentration at a certain level, we need at some point to make sure that it actually going down. Otherwise the temperature will be still increasing, and it's really dangerous. So by the end of the century we need to reach net zero. And another question, how much we can still emit in order to match with those limits that we set in the Paris Agreement. So if the calculations were made several years ago, so probably we already used a little bit of those budget, but it's more or less like that. If we need to stay within 1.5 degrees centigrade, then we can only emit into the atmosphere something like 400 billion tons of CO2. And if we are emitting something like 40 billion tons annually, so we only have 10 years, but basically less than 10 years, because the calculations were made like 2-3 years ago. So at least a certain part of that was already gone. It's like something like 320 billion tons on aggregate. That's why we are focusing that closely on what has to be done within this particular decade. This decade is called sometimes like a decisive decade. We need to really be focused and do a lot in order to reduce the emissions as much as possible by the year 2030. Now, if we consider 2 degrees centigrade rise in temperature as the maximum, like kind of allowable, so to say, then we have 1.1 trillion tons, right? Again, if we divide by 40 million, then it's more or less like 25 years, which means that by the year 2050, we still have to do something. Otherwise, the temperature will be, increasing and increasing and increasing, and we will be like boiling here. So there's the routes or trajectories depending on how much we are emitting and where we will end up by the end of the century. So in order to keep the temperature rise within 1.4 or 1.5 or 2 degrees centigrade, only the lower two trajectories are allowable. So which means that actually we need to reverse the trend, and instead of growing, instead of allowing emissions to go up, we need to do whatever we can to get them go down as quickly as possible. Otherwise, the temperature will be rising. So this is red part or pink part actually means that if we fail, then by the end of the century, the temperature would be something like 5 degrees centigrade higher than in the pre-industrial level, which is like crazy thing to happen. Now, if we try to look more carefully at the sources of emissions, then on your left side, you can actually like see that the source of emissions actually the burning of fossil fuels mostly. Little bit also comes from the fugitive emissions, again associated with the extraction and transportation of fossil fuels, and something a smaller part actually relates to the production of cement. But mostly, the biggest part of emissions is coming from the burning of fossil fuel, coal, oil, or oil-based products, and natural gas. Now, on your right-hand side, then the same emissions, but detailed by the regions. So at the beginning, it used to be like US and other developed countries, but now this is not. The biggest part actually belongs to China. So now the biggest emitter of greenhouse gas emissions is actually China. The US is second, India is third. All 27 EU countries are fourth, and Russia is actually fifth, more or less. But because I mentioned that basically not emissions are the driver for the temperature rise, but actually the concentration. So we rather need to consider the aggregate emissions over the period starting from the Industrial Revolution. So here's the graph demonstrating more or less how it was growing over time and the contributions of different countries in this long run, so to say, in terms of emitting CO2 into the atmosphere. And this yellow circle is actually demonstrating how the carbon budget is diminishing over time, right? So it was at certain point, if we again mean 1.5 degrees centigrade rise in temperature, it was certain amount. Then over time we are kind of using it, utilizing it, and it's actually decreased. So we only have what we have. And so in terms of aggregate emissions, US is in the first place, China second, Russia actually appear to be third. Now, a little bit in more details, if we look what sectors are kind of responsible for the emissions, then we can easily, first of all, see that the emissions are divided by, like, for energy related and non-energy related. So energy related are those that are actually associated with the burning of fossil fuel, but also with their extracting and transportation. And non-energy related, it's like when we are considering industrial processes. For instance, if we add carbon or materials that contains carbon, then within the processes, this carbon actually escapes in the atmosphere. Probably it's like chemical industry first, but also iron and steel, and then aluminum. And I would probably say that those that are not energy related emissions, mostly this is not CO2. I also mentioned that there are some other greenhouse gases apart from CO2, particularly N2O, then methane, then hydrofluorides, then perfluorides, and some other. It's like difficult to pronounce. I can put the formula on the desk if you need. But those that are related to industrial process and agriculture. Agriculture is the biggest emitter of methane. Waste management, again methane. Wastewater treatment, again methane. Chemical processes, all this so to say, F gases, and a little bit of CO2 as well. Production of food, actually, with the food production, we have like more or less quarter of emission associated with this particular part of our activity. And the bad news is more or less like 6% of emissions is the food that we actually wasted. So never used it. So we produce it, but never use it. So it's like probably the biggest source of, saving products and saving emissions is by reducing the waste. Now forests, we also cut forests, and it normally in the real life, forests would absorb, of course, CO2 and get it like stuck in the wood, but we actually tend to cut forests. And if you think that we do it because we like to read books, then you have to think again. We actually like to eat meat. That's why we are cutting forests, basically, not for producing paper, but for producing beef, mostly. Now, because the Paris Agreement says that we need to go down by zero by the mid of century, then we have kind of a race of the countries in setting the end year of this period, right? So most of the countries say that they would go to net zero, like literally by 2050 or even earlier. But some countries decide that middle of the century does not necessarily mean 2050. So Turkey says 2053 for whatever reason. China, Kazakhstan, Indonesia, Saudi Arabia, and Russia says 2060. Thailand says 2065. India and Ghana even 2070. So 2070 still sometimes is considered to be like mid of the century for whatever reason. But anyway, so far we can actually see that 80% of global anthropogenic emissions are kind of restricted, at least politically. So there's a certain point in time where they need to be balanced by removals or avoided at all. Those countries that also already have targets, they cover 80% of global GDP and 85% of the global population. So we can actually say more or less that politically, in terms of like setting targets, we have most part of the emissions already kept, right? Which means that the second step should be now done is to, practically implement those intentions and to do something in terms of, switching from high level emissions to low level emissions as was anticipated in the Paris Agreement. Now, what are the factors actually drive emissions? There are different approaches in the economic theory, how people would treat. I put here two different, like very simple models, which actually say that emissions are actually a function of the population, then GDP or per capita, and then like technological factor, which is emissions per unit of GDP. This is the simplest model. A little bit more difficult one is saying, okay, this is not completely about just GDP as it is, but basically it's because people tend to consume a lot. And that's why we need to actually kind of see how much they actually tend to consume, and then to associate emissions with the consumption. I don't like this theory at all. But anyway, this is what people used to say, and they actually try to blame Novorishus, so to say, Novorishus, for their over consumption over time, which I don't like. Basically, I don't like the theory of personal carbon footprint. I think this is a very false concept. But anyway, it's not about that. So let's probably take like more practical approach and say, okay, as we mentioned, the emissions are like combined of energy related and non-energy related. So let's see what energy related emissions are connected with. Again, we will follow the same tradition. So we will put population first, but then instead of GDP, let's say it's goods that we're not consuming GDP, we are consuming goods. So let's say that the second factor would be goods per capita for one person. Then in order to consume 1 unit of whatever good, we need to use a certain amount of energy to produce those goods from the raw materials or whatsoever, but also we need energy to consume. For instance, if we are consuming all these devices, then we also need energy to be able to consume. Or if we drive car, we also need energy, right, to make the car actually go. So EN is kind of a specific energy produced and consumed to be able to consume one part, only 1 unit of GDP of goods. And then the last part would be, of course, the emission factor. So what we are actually emitting per 1 unit of energy that we are producing, right? So this is more or less in terms of energy related emissions, more or less the same in terms of non-energy related emissions. Again, we are producing something in order to actually sell it to the population and have them consume, right? So we have population first, goods again second, but also we have like, we don't need energy for this part because there's non-energy related. So we have like emission factor for 1 unit of goods produced or consumed. This is more or less the same. So now if we put all this together, then we will see this, the final formula, which says, okay, it's P and G, but also in the brackets would be emission factor per 1 unit of good multiplied by the emission factor, and then emission factor just by 1 unit of goods. So basically, if we see this here, right? PG, what can we do actually to get it down? Let's see factor by factor. This is population. Do we have any chance actually to reverse the trend? So the population is increasing over time, and it will still be increasing unless a certain disaster might happen, but we would do whatever we can actually to avoid, right? So we can do a little bit with the fertility factor. And the biggest thing we can do is actually educate women and put them into the social activity. This is the only one that actually works well, not anything else. Now, in terms of wealth, so in terms of amount of goods we tend to consume, again, we are the civilization of consumption by far. So and there's no limit. We can still consume and still consume and consume even more, and we still have a lot of population actually living below the level of poverty. So we really need to do something with those poor people, right? So in one of the targets of sustainable development is actually avoiding poverty, right? So that's why that overall average consumption of goods will be still increasing over time, right? And we also have this and had it forever, and so not a lot to be done with that. Again, we can still claim that certain groups, like this new rich people, can actually stop their like demonstrative consumption, but rather do something like more modest and reasonable. But this would not change the general trend. Probably a little bit the pace, but not the still the trend to grow. Now, energy intensity. Again, let's see this formula. Okay, this energy intensity, right? Yeah. Yeah, we can do something, and people tend to say that this is probably the biggest part we can do actually to use less energy than we were using so far. But the tricky thing is that once energy is not a limiting factor, then we would actually tend to produce and use more goods. And there's probably two exceptions for that. It's like energy that we use for heating. We would not overheat our premises for sure, right? And cooling, and we will not overcool our premises for sure. So we will keep the comfortable temperature. So probably the heating and cooling of residences and administrative buildings is probably the only one, or only two, so to say, right? Spheres where energy intensity can be really reduced, and this will end up in reducing of the amount of fuel we are using. But the carbon intensities is opposite to that. So basically, again, let's see the formula here, right? It's carbon intensity of energy production. This is carbon intensity not related to energy. So what we can do with this? Of course, we can switch from fossil-based energy production to non-fossil fuel-based energy production, like wind, like solar, like hydro, like tidal, like whatever, like geothermal sources, so and nuclear, of course. Nuclear, nuclear, of course. Basically, in all the scenarios for switching to low carbon emission energy, nuclear is mentioned. But as far as I remember, even in the best scenarios, the share of nuclear is less than 10%. And the main reasons are not only safety, but also timing and costs. So it's much easier actually to build solar and hydro and wind rather than to build new nuclear plants. And that's why the focus so far is on producing and on building new capacities of solar stations and wind stations. They are the cheapest on Earth so far. as energy sources. With non-energy related carbon intensity, there are some troubles. It's not much that you can do in terms of agriculture, because the internal how they call it metabolism, right, so to say, of animals is still in place, and you cannot avoid it at any time. Now, in some industries, like for instance chemical industry, it's not much that you can do. If you still need like nitrogen, so anyway, N2O will be still escaping anyway, right? So if you need like fertilizers, then N2O would be escaped from the land when you put the fertilizers into the ground to help the crop grow. So anyway, it's a little bit harder to deal with this part of emissions. And that's actually what we need to use our ability to absorb emissions from the atmosphere for, right? So we can do whatever we can, or we should actually do whatever we can to avoid completely emissions from energy, and then to use the potential to absorb emissions for those part of emissions that are not avoidable, like heavy industry and agriculture, and maybe waste a little bit to a certain extent. And wastewater treatment, if we use certain technologies for wastewater, or we can actually still use wastewater treatment as an additional source for energy production if we use methane, right there. And there are some examples where people does it. Now, the decarbonization of energy is very simple. We need to switch from the gray part to the green part, which is easy to say, but not that easy to do. But we have certain trends already in place. So over time, the investments into green energy are really, really increasing rapidly. And last year, the amount of money invested in green energy and in fossil energy were more or less the same for the first time ever in the last history. So probably next year or in the coming years, we will see the reverse trend. So the investments in the green energy will be higher than the non-green energy. This also the increase in power generation, and we see that like this blue lines, so to say, right? This is the addition of non-fossil energy sources, and the gray lines is like fossil-based energy sources. So we see that starting from the year more or less 2012 or 13 at least. So the general electricity capacity in the world is increasing due to the green sources rather than the non-green sources. But to actually have the trend called energy transition, basically, we need these gray lines to be negative rather than positive, right? That would actually mean that we will now have the substitution of fossil-based energy for non-fossil-based energy. But this is not happening so far, but it's more or less close to that, to that point. Now, in terms of road vehicles, it's like running away from the internal combustion engines to the electric cars. And basically, we have very obvious trend that investments and spendings on buying electric cars is growing over time. And of course, the sales of vehicles is also growing rapidly. And in the sector of light-duty vehicles, the cost of holding the electric car is now lower than the cost of holding the internal combustion engine-based vehicles. And the middle to heavy duty cars, that's probably will happen within the 2 or 3 years. So basically, that would mean that it's easier and cheaper to have the electric car even in the for transportation rather than just driving. And this would be like the complete game changer. In terms of the share of electric cars, the first place is now Norway. So the share of electric vehicles in the sales per year is something like 90%. In China, it's growing rapidly, and if we consider the total amount of electric vehicles sold, then China is by far the leader of the world. Now, in terms of aviation, we also have at least the decision made by the Air Transport Association to go down to net zero by the end of the 2050, by 2050, so to say, right? And we also have in place the system which is called CORSIA. It's carbon offsetting and reduction scheme for international aviation, administered by the International Civil Aviation Organization, which is the UN structure, so to say, right? And so they also have this. First of all, they claim that the aviation company should offset the emissions by removals or by other kind of carbon units, and they also introduce the standards for aircrafts. So in order to be able to actually use the aircraft, so those aircraft should meet a certain standards in terms of CO2 emissions per 1,000 kilometers of flight, so to say. So basically, they are covering to a certain extent emissions associated with the aviation by different types of regulation on international level and also domestically. So it's kind of also kept. And now in terms of shipping, the idea also would be to switch from oil-based fuels that are normally used in the sea shipments to something new. It can be they call it e-fuel, so it's like more or less green. It's based on methanol or something like that. So it's kind of biofuel or synthesis fuel that is produced specifically to avoid emissions during the shipment. Industries, probably the best idea for at least some parts of industry would be to switch to hydrogen. And we have already some interesting examples when the steel making plants are switching from using carbon to using hydrogen instead. It's like direct, what they call it, the process that actually help avoid the production of pig iron first. So they produce steel right from the ore, so to say, using hydrogen instead of carbon. And then the other good idea, probably not the final one, but kind of an intermediary, is to use CCS, which is carbon capture and storage, or carbon capture and usage. And some plants in Germany, at least, they are looking very carefully at those opportunities. The idea would be to capture exhausted gases from the industrial processes and converts them into the liquid fuel or fertilizers or plastics. And because during the steel making, actually a lot of CO2 is actually formated, then it's even economically viable thing to do. But finally, they would still like to completely dismold this old-fashioned technology and to introduce new one based on green hydrogen. And green hydrogen is that type of hydrogen which is produced using green energy, as simple as that. And then probably the final slide here, are we actually on track? No, we aren't still. And we need to do really much more within the coming years in order to be on track and to reduce emissions to the levels necessary. Should be minus more or less 40% from the level 2019, basically. And we are not on track yet. So we still have something like between 15 and 20 billion tons in addition to what we need to have by the end of this decade. And in this regard, I would probably mention the recent declaration made by China and the US, It was done like 2 days ago, something, where they say that they would actually cooperate closely to make this happen. And why this is very important, because actually the US and China are two biggest emitters in the world. So if they are responsible together approximately about like 40% of the anthropogenic emissions worldwide. So if they really manage to do something in terms of, reversing the trend and really decreasing the emission, then that would be actually a big contribution into the global battle with the climate crisis. Thank you very much. You have any questions? I'm available to answer.
Thank you very much, dear colleagues. Any questions? Oh, okay.
Thank you very much for your experience and expertise. I want to ask about those clean technologies.
Clean technologies, okay.
Yes.
Like what?
Nuclear, actually.
Nuclear?
Yeah, of course.
Okay.
So from my own project, actually, I am working with the steam generator, and right in my project, I want to actually make a little defense for nuclear about the CO2 emission and all this. So how can I go from the energy point of view to make my dissertation very clear and plain? Thank you.
So what the question is?
Okay, in the clean energy technologies, how can you explain or shed more light how nuclear can be much more efficient for eradication of CO in the atmosphere to meet the Paris Agreement also, something like this?
Well, first of all, I did mention nuclear among the low carbon sources of energy production. So this is for sure, right? We have at least one big study made by IPCC back in maybe 10 years ago, something like that, where they compared the carbon footprint of different types of energy. And basically, by that time, like 10 years ago, the carbon footprint of nuclear energy was the one of the lowest, basically, right? Because whatever you need to produce the fuel and then to run the mill, actually you only need the energy, and this energy can be greened, very easily. But actually you can do the same also for wind and for solar. And at least we have this company which is called Havel in Russia, and they are big solar panel producers. And they started to install the solar panel actually to supply energy to their own facilities, their own premises, where they produce those panels. So they cannot actually still do it for the premises where they get the raw materials from. Okay, so those guys are still using the fossil fuel to run the fields, but like all together, the solar and wind are also like very, very low carbon. And then if you consider the relative advantages, then of course for nuclear plant you have an opportunity to produce at one site more than actually wind or solar stations can do. But again, the trend so far is like the per unit capacity of wind stations are increasing over time. And now, since there is an opportunity actually to build on platforms in the open ocean, and many companies started doing so, so there's probably no limit for capacity to be installed. And I know already the wind farms and the wind turbines with the how they call it. No, I mean the diameter, something like 200 meters already, so something enormous. Yeah, this stuff. So they asked, they like the circle would be like 200 meters in diameter, something astonishing. And then the biggest solar plant constructed all at once, I guess, was quite recently launched in Saudi Arabia, and it's 2 gigawatts for just one station, and it's more than Russia has altogether. Right, so they have at one place 2 gigawatts capacity, which is more than Russia have all over its territory. So again, it's still a chance basically to increase the capacity of the renewable energy. And again, another. So basically, those like relative advantages of nuclear kind of disappearing over time, as far as I can see. And the disadvantage of nuclear is like timing. So you need a lot of time actually to make agreements with all the stakeholders. And it now takes a very limited actually time to get the consent of the stakeholders if you build solar or wind. And basically in Europe, they now introduced a new regulation saying that in a certain part of countries, it should take no more than like 6 months, but 12 months as most in any case. And this is something which nuclear, projects cannot achieve at all. So it takes years in terms of discussing and coming to terms and stuff like that. And then it takes again years to construct. And sometimes it takes even more than it was projected. For instance, if we consider the recent project in Belarus, then it takes like 2 more years than it was initially anticipated, which also is not very, saying in favor of nuclear, but rather in favor of something different. And still the neighbors are complaining. I mean, Litva, they're not happy at all that they now have close to their borders a nuclear object. So basically, I would not tend to say that we have to stop building, but I would try to say that we should not overestimate the opportunities of switching totally to nuclear. We should consider many other different ways to produce green or clean or low carbon energy. However, we all know very well that wind and solar and all that stuff are kind of not stable over time, right? So it's like a big distortion between the time period when they produce high and the time period when we need to consume high, right? So there's like a mismatch. So we need kind of intermediary storages to be able actually to get all the benefits from producing green energy. And for their storages, we can consider again 2 different technologies: batteries, like Tesla batteries, for instance, which are now built, for instance, in Australia, or we can consider hydrogen or hydrogen-based leakages that we can also use as a storage for energy. They are transportable, they are storable, so to say. So basically, hydrogen can not only be used to decarbonize industry, but also kind of an additional agent, so to say, that would put together the energy system based on renewable sources, which are not stable over time, right? So, and this is why we have a lot of investments now being forward, so to say, into the hydrogen economy, meaning that at some point, hydrogen as a basis for transportation, or for instance, for shipping or whatever, aim for aviation, but also like a storage agent for the electric power, should be in place and should be affordable in terms of costs. Okay.
Thank you very much.
Thank you.
Thank you, Michael.
Thank you. Bye-bye.
So, dear colleagues, we have a legal break.
Good morning, Андрей.
Михаил Иванович.
А,
Ну, буквально
Доброе утро, Андрей. Добрый
несколько
день,
минут
Андрей.
и
Вы
продолжаем.
дайте мне возможность раздать экран. У меня пока такой нет возможности.
Не слышно вас.
Сейчас.
Секундочку.
Я вас слышу.
Нормально. Сейчас, подожди. Все, Михаил Иванович, а можете еще сказать что-нибудь?
Я вас
все,
слышу.
все,
Вы
все
меня
отлично
слышите?
пошло. Да, все отлично.
Дайте мне возможность раздать экран, пожалуйста.
Да. Все готово.
Ага, спасибо. Появилось?
Да, все отлично.
Все, отлично. Хорошо. Ну, как вы мне скажете, когда начинать?
Да, буквально там пару минут.
Хорошо, хорошо. Никаких, я свободен, никаких вопросов. Скажите,
Хорошо.
между двумя лекциями 5 минут, наверное, резонно сделать?
Ну, я думаю, что да, можно 5 минут.
Хорошо, я сделаю, я сделаю.
Спасибо. So, Michael, are you hear us? Yeah, okay. So, dear colleagues, please take your seats. We continue from the next presentation. So, it's Michael Ajavan, Imperial College London. So, he will told us about classification of nuclear waste. So, Michael, floor is yours, please.
Thank you, Andrei. Many thanks, Andrei. Good afternoon, everyone in the room. I hope that you see the screen and you can hear me. It's still morning here in Europe. Nevertheless, it's already the day, working day. So let's move. I have to give you today two lectures. So the first one is classification of nuclear waste, and the second one will be about norm waste, not just norm waste. Perhaps we will make a short break in between, and about the questions, I don't know how Andrei will arrange them. Perhaps it's better after the first lecture to put, and then after the second, but it's up to you. Let's see. So my first 45 minutes from me, I'm teaching to students, so I try always to keep the schedule. I will try to do here as well. So not more than 45 minutes for the lecture, and maybe some questions. So let's see. So the first one is about classification of nuclear waste. So you see that the school is on ecology, and the civilization is so powerful that it's producing through industries and through normal life a lot of waste. And the nuclear industry, nuclear energy, use of nuclear energy produces nuclear waste, or we say radioactive waste, which are synonymous. And since we need a kind of language to understand each other, what kind of waste are we speaking about? We say radioactive waste, we say nuclear waste. And even within the waste can be everything. Can be spent nuclear fuel, which was used in a reactor, and the United States prefer to say used fuel. So the fuel that was burning in a reactor, and after it's irradiated fuel, also a kind of term. But can be even a piece of paper that was in an office for an employer at nuclear power plant, and is just declared radioactive or nuclear waste. And then it passes through a procedure which is called clearance. So it is measured whether it's really radioactive waste or not, and typically not. And there is just waste, not radioactive waste. So let's focus on radioactive waste, on nuclear waste. And I was introduced. You see here my affiliations, and my pointer is working. You see here I also lead as a chief editor the Journal of Science and Technology of Nuclear Installations, open access journal, one author, if not the most influential journal of nuclear industry. So since here in the room there are researchers, advanced researchers that work in the area already in the nuclear sector. So you are welcome to submit the results to share with the experts. So, oops, why is not working? Once again. Oh, now it's working. So this is the content. So several sections about. Let's move through them. So I'm starting with the background information. So if you work in a nuclear sector, then there is you know that International Atomic Energy Agency is publishing advisory documents, technical documents, guidance documents. Is publishing also standard series documents, standards, which are internationally recognized. So they are really fundamental standard documents to follow. Very reliable, and that puts a kind of framework on international scale. So you can see here the cover of a standard, which the previous version, because it's updated, republished. That one was republished in 2014, and it was called before that BSS, Basic Safety Standard. It's a kind of Bible in the nuclear area. And again, many of you may know, many may not, that you can download from the IAEA website all IAEA publications for free. You download them and then you can use them. In print, you need to pay for them. So This is a Bible. So the basic safety standard, it has the title General Safety Requirements Part 3. It has all kind of requirements if you work in nuclear sector. It's very good to have it on the table, and has the definition what is radioactive or nuclear waste. What is that? Because waste, more or less clear, is the material that no use, nobody needs it, no wanted material. It's a waste. But now we speak about radioactive waste or nuclear waste, right? So you see here the text, this definition. So it says that it's for legal and regulatory purposes, material for which no further use is foreseen, that contains what is contaminated with radionuclides at activity concentrations greater than clearance level. You see, I underlined that, I emphasized that, right? Established by the regulatory body. So, dear colleagues, that is the definition, and it says for legal and regulatory purpose because everything around us, including ourselves, our bodies, we are a little radioactive. We also contain radionuclides in the bodies, and everywhere, in the walls, in the floors, and all kinds of materials. So if to be strict, then all the waste should be radioactive waste because they contain some radionuclides. You know, this carbon-14 dating that we can identify when a plant, an organism, living organism, has passed away, died, it's not anymore functioning, and after that, the ratio in between the stable and unstable carbon-14 is disturbed, because until we are alive, the ratio is constant because we are living. We are replacing the decayed radionuclide in us by the new portions that are coming to us. But when the organism is not anymore functioning, then no more income of carbon-14, and we can identify by the ratio between unstable and stable when the organism passed away. So this is carbon-14 dating. So once again, the definition. You know, there are some clearance levels. It should be a large lecture to have some talk about these clearance levels and so on and so on. Now just take it as a statement. There are some clearance levels, some concentration of radionuclides that are approved in each country by regulatory authorities. And if in the waste, the content is higher than clearance level, then only in this case, the waste is radioactive or nuclear waste. Only in this case. If it is below, we say that this is cleared waste or exempt waste, and it's not the point of a regulatory authority, which is nuclear regulatory authority, so radiation protection authority, and so on and so on. So again and again, everything around us from the beginning of the universe, it's radioactive. It's radioactive. The question is, what is the level of radioactivity? And because of that, actually, we need for now the radioactive waste classification of radioactive waste. This exemption, clearance levels, exemption levels, a reminder, because the information is taken from the Bible, from the basic safety standard. So it was internationally agreed, and this is a convention that is still followed, although it is extremely conservative. It is unjustifiable conservative, and there are discussions to change. And my next lecture will be about the norm, naturally occurring radioactive materials. And you will see that this very conservative level is different from that one that is here. So it was agreed, and now is followed everywhere. It's recommended by IAEA. IAEA means International Atomic Energy Agency. ICRP and all kinds of international organizations, and it's followed in all the countries. So it's taken that if during 1 year the expected dose is 10 microsievert or less, then no reason to consider this material as radioactive. So conventionally is non-radioactive, although as scientists, as maybe employed in the nuclear sector, you understand that some radionuclides are in there. But if the expected dose is not higher than 10 microsievert per year, entire year, then if it is not higher, this is non-radioactive material, is it exempt, and that's it. The story is not for us. It's for other regulatory authorities. So maybe there's some chemicals there, some biological, toxic, and so on and so on. So it doesn't mean that we don't care. But regulatory authority exempt this material from regulatory control, and you can work with these materials, you can consume these materials, you can do everything that you like. So remember this number, 10 microsievert or less in a year. So if it is above, then practically everywhere there are some clearance levels, and if you find that the radionuclide in the material has the concentration higher than these that cause this 10 microsievert per year, this is radioactive waste. It's important for understanding what do we speak about. So once we are above these clearance levels, the waste is radioactive waste, so does not pass the clearance procedure, let's say a paper from a nuclear office in a nuclear power plant, or maybe it's a real spent ion exchange resin, something contaminated, so on and so on, and we are getting to the activity that is called radioactive waste management. So it's not waste management, it's radioactive waste management. And in radioactive waste management, you see that we have here in the picture, it's shown, it's a schematic. So we have radioactive waste management that typically is divided into two parts. The one is called pre-disposal radioactive waste management. And you see here many activities in pre-disposal radioactive waste management. So we have processing of the waste. We need to store the waste. We need to transport the waste. And in processing, it's pre-treatment, treatment, conditioning, so many things we are doing there. And another part, big part, is called disposal. So it's when we put in a dedicated facility, and it's like, forget about. So everything is prepared in such a way that if you put there, if you dispose of, then we ensure that there is no any harm of the environment and humans. So pre-disposal and disposal, these are operational activities, things that are done with the materials. But there is also a large part of activities that are administrative activities. These are under the so-called, management systems. So we need to plan radioactive waste management. We need, of course, to understand what we are dealing with. So establish an inventory. Then we need, this characterization, so to measure something and so on and so on. We need to have some waste acceptance criteria for all facilities, for the disposal as well, for transportation. Not everything is allowed to be transported. We need to ensure that something is prepared properly to safely transport the material, and everywhere is the same. Then we have technological processes, here developments and so on. The cost estimation, we are trying to save the funds that we are spending on radioactive waste management. Licensing, waste management operations, and so on. So we are coming to the point that we need classification to understand what we are dealing with, what and what we are speaking about. So this here, I will show you this picture later, then you will understand the classes, and then you will understand what kind of waste it is where. So we need to plan, right, in the administrative. We need to identify the hazard in the waste. We need to give some guidance for operators. Should they care about the shielding or not, and so on. Uniformity through all the life cycle, because the life cycle of the waste, it's very long, really. So in the radioactive waste management, we are starting to speak about even millions of years. It's absolutely unbelievable. Because for more older people like myself and so on, we can see that even during 10 of years, many things drastically change. And then we will try to predict the behavior of the materials for thousands of years or even beyond that. That is extremely difficult task. Clarity. So if I'm telling to you something, you understand what I'm speaking about. So if I say height, maybe this is not the height, maybe it's, and so on. So it's very different height in radioactive waste management and, in construction industry and so on. So for communication in between us and other parties, for comparison, what's happening here and there, inform policy and strategy, and record keeping, because the people are aging and so on. So then we transfer the information to the new generation and so on, and in between us and so on. So the records should be kept so that sustainable. So that's it's needed to have classification of radioactive waste. And as purposes of radioactive waste classification, you can see here a table where the left column says about aspects that are provided. So the first one, let's say, it provides essential input for national radioactive waste management policy and strategy. And we are replying to the question about how much waste do we have and what kind and size of waste management facility we need. Because of that, we need to have classification. Terminology well understood that adds communication. And then again, the question, this is classes such as we will speak about low-level waste, so that we conduct those rates, it's not more than, and there are some numbers, then gives a broad indication on potential hazard, so that appropriate decisions to be made at each step of life cycle management. And again, the question that answer, can we handle this waste manually, or we need to employ some remote techniques, maybe to have some shielding. Systematic foundation for waste segregation and management programs. This is really, really a very substantial claim, because if you say that this is high-level waste, then all activities becomes extremely expensive, difficult extremely, and expensive extremely. So that's the question that answers. Indicates the disposal route for this waste and efficient management system for operators. And now, ways to classify the waste. So the classification that I will introduce to you now, it is the International Atomic Energy classification, IAEA classification. But before coming to that, internationally recognized and nowadays practically everywhere used to a certain extent, how can they classify the waste? First of all, by origin, right? This is waste that is generated, let's say, during operation of nuclear power plant. And then it's waste, let's say, from power generation. Because can be reactor, which is a power reactor, but maybe it's a research reactor. Maybe it's a facility in the nuclear fuel cycle. We have nuclear energy use in medicine, in diagnosis and therapy. In research, even in education, in industry, we have irradiators. We have naturally occurring radioactive materials that we will speak a little bit later. Then by physical state, very, very important to know, it's solid, liquid, or gas. Radionuclides, we speak about decaying radionuclides. So the half-life, maybe that they decay very, very quickly, in maybe days, maybe months, but maybe they are long-lived. Different situation. So we need to know that. So we say short-lived waste or long-lived waste. And by activity concentration. Can be that activity concentration, like in high-level waste from reprocessing of spent fuel, it is extremely high. So, but maybe that is very low-level waste, which often is not much. It's very difficult to distinguish against the background for very low-level waste. So in order to identify the radionuclides, we need to apply insulation, because otherwise we cannot measure, because the radiation from the ground is higher than radiation from the material that we suspect that is radioactive waste. So that's normal in the commission project. Then for clearance, these chambers or the materials after the commissioning are passing through to detect radionuclides are insulated from all the parts to protect against cosmic radiation, background radiation from the walls, from the floor, from everywhere. So that's different. So by activity concentration as well. So how to be? So in different countries, historically, different schemes were developed. International Atomic Energy Agency tried to combine experiences in all the countries in the world, inviting experts from everywhere and considering all kinds of options of classification. And finally, it has came to a generic IAEA classification scheme published in 2009. You see the cover, you see the document. This is a General Safety Guide, GSG1, published in 2009. So this is a conceptual waste classification scheme that gives advices to member states, and nowadays 174 countries in the world are member states of IAEA. So they are members of IAEA community, so they are eligible to receive any kind of assistance through IAEA, where the IAEA is sharing the best experience in the world to all participants of IAEA. So the schematic of this classification, so that's a book, this guide. So it's a lot of text there, definition, some parts, just some parts I will share with you. But this is a schematic that shows the principle. So as a principle, it was decided, and from 2009 it is used everywhere, that as the main parameter for classification will be used the final endpoint where the waste is going to be disposed of. The endpoint, it is called endpoint, as the target everywhere. So then this endpoint, it is here plotted in terms vertical scheme activity concentration. So this is a generic term that can mean concentration, so it's becquerel per gram, and can be the total activity. So maybe just amount of becquerels or in all the system QD, the total activity of the material, like a spent or used radioactive, disused sealed radioactive loss. The total activity can be huge and concentration high. And another here horizontal line. That is half-life, because it's one thing to deal with the very short-lived radionuclides, and another to deal with the long-lived radionuclides that are on the right side here. And if you go into vertical direction, you see here the first one is so-called exempt waste. It is where I just spoke to you about these clearance levels. They were derived using the criterion 10 microsievert per year. So each radionuclide has this criterion, and these are here for all the radionuclides. Then we have very low-level waste, intermediate level waste, and high-level waste. And in this part, we got very short-lived waste. This is another picture, maybe a little bit easy to look at it. So if we speak about the highest by activity and long-lived, then we go to deep geological disposal. If intermediate, we go to intermediate depth disposal. These are recommendations, generic recommendations. It doesn't mean that you go deep geological and you are safe. You need to look there. What kind of geological? Maybe it's aquifer. It's very deep, but the water is flowing there. Then no way to stay there. And the same is everywhere what it said. So that's kind of generic recommendation that should be followed, and then within this recommendation to look on a real suitable site. So it's not just the depth gives you the full protection. No. So low level near surface disposal. And you see here very low level waste, landfill disposal. And in reality, that goes this industrial waste very often, very low level waste. And this level's exemption, so it's not aligned. Each radionuclide has its clearance level. And these are published in BSF, in this Bible that I just noted. And these are exempt waste. So radionuclides are there, but they are below clearance levels, and we say they are non-radio. But we understand there is some radioactivity inevitable there. And there is a line here, which is called, here it's named 30 years. This is actually the half-life of cesium-137. So including cesium-137, if by half-life, if the radionuclides that in the waste are here in this part, their half-life are shorter than 30 years, we say this is short-lived waste. If longer, we say long-lived waste, but the definitions are really in this slide. So we speak about short-lived waste and long-lived waste, two types of the waste. Short-lived, you see here that half-life are not greater than 30 years, and if some longer-lived radionuclides are there, their concentration must be non-significant. So the content low. And there are some even indicative numbers. You see here the limitation on concentration, 4,000 becquerel per gram in one individual package, or average per the whole repository 400 becquerel per gram. So that's according to this IAEA document, right? And if the content is higher than these numbers, then we speak about long-lived waste, long-lived waste. And this is because we say short-lived waste can be disposed of in near-surface repositories. And long-lived waste should go deeper, maybe intermediate depth or even deeper. That is because the near surface during hundreds of years, very significant change will not occur. But if the half-life is longer, then we see that, the river are changing their flows, flooding, shifts. Many things happen on the surface naturally. I'm not speaking even about human activities that are also significantly give a significant impact on all kind of what's happening on the surface. So definitions of these classes now. So we speak about class. The first one was exempt waste. So we say like is non-radioactive waste, but we say exempt waste. So it's not under regulatory control of nuclear or radiological authorities. Because of that, it's like non-radioactive waste. It's not our topic to discuss. Then we go to by the half life to the we see very beginning here with the so-called very short-lived waste, very short-lived waste. And the definition it is that we can store this waste for decay. Then naturally we will decay over a relative short period of time, and just keeping this waste naturally the content of radionuclides will become below these exemption levels, and after that we will say, please, authority, clear this waste because it's not anymore radioactive waste, it's this exempt waste. And the authority will check that and ensure that everything is obeyed, and we will receive the permission to clear this waste from regulatory control and consider it as non-radioactive material. So that's actually here, according with the text presented in the safety guide. Then we go to the very low level waste. So what is very low level waste? I informed you that we have this very conservative criterion of 10 microsievert per year. It's extremely conservative. And if the content is a little bit above this, so it's instead of 10, maybe it's 20, maybe it's 50, maybe even 100. But if you compare with the background radiation, which is 2,400 average on the Earth, in some places is 10,000. I don't know, in Moscow, maybe there are some devices that show the background radiation. But this 10 microsievert, it is even less than error bars. You cannot even measure it because the background radiation fluctuates. So it's extremely conservative. So if you are a little bit above these clearance levels, we say that this is very low level waste. This waste does not need much care, no containers, no. It can be in a bag and can be even disposed of on landfill together with other waste, industrial waste, because there is no real hazard from radionuclides there. So this is very low level. Then we move to low level waste. If the content is much higher than the clearance levels, then we see that this radioactive material is hazardous. But the content of long-lived radionuclides is restricted, and this waste does not require confinement somewhere for thousands of years. It needs several, maybe hundreds years, maybe even less. And in this case, we can rely on near-surface facilities to dispose of this waste, providing all kind of shielding, all kind of containers, feeding materials, and so on and so on. But on near surface, during several hundred years, since we know the behavior of materials for hundreds of years, we have buildings that are constructed by humans. We have materials that are we know their history, how they behave, how they corrode, how they decompose, and so on and so on. And we can rely on our knowledge for several hundred years with very high confidence. And because of that, this waste is permitted for near surface disposal. And the nature, how things happen on the surface, again, there are predictive models, so safety assessment is, of course, always provided. So this is low level waste. It is allowed, you see here, for near surface disposal. Then, in the cases when the content of long-lived radionuclides is above this you see here, it's again repeated. You see this per package 4,000 becquerel per gram. And on average is 400 becquerel per gram for long-lived radionuclides, not for short-lived. Then we say it's not safe to dispose of this waste in near surface repositories. Because if you go beyond several hundred years, if you go to thousands of years, you understand that many changes occur on the surface. And due to natural events, tornado expected, earthquakes, change of the river, aging of these materials, corrosion, decomposition of these materials, and so on. We need to go deeper in such layers under the grade that there these changes do not occur. So the agency recommends that we should go at intermediate depth, or if such a possibility exists, even in deep geological disposal. So maybe some unused mines are available, then why not to go there? It depends, but not to be on the surface. We should go deeper. And in this case, we speak about intermediate level waste. Agency is recommending this number, 4,000 per one package. So many packages can be there, some of them much less, but on average, it should be not more than 400. And in many countries, these numbers are taken in regulatory documents. But in reality, these numbers are not given, from the Bible, from the God, and so on. These numbers, they're obtained, calculated based on safety analysis report. And they are a kind of generic and again, conservative. In reality, it shall be a safety analysis report, and in many cases, these numbers can be much higher than these recommended. The question is that through the safety analysis report, we should ensure that the population around in the place where is this and far away as well will not receive those burdens that are higher than those recommended by regulatory authorities. So, but in many countries, these numbers were taken as they are in IAEA and are used. And if it is a question of a small industry, small country, not large use of materials, then for with great confidence, we can use these numbers as conservative and good to be followed. You see here that comment about. So this is, you see, intermediate level waste, intermediate depth disposal. And then we go up by the content of radionuclides, and we are coming to high level waste. High level waste, no way to dispose this waste even at intermediate depth, because this waste needs an extremely long time of insulation. The question is about many thousand, 100,000, even millions years, because the radionuclides there, the content of long-lived radionuclides is such that they will decay to the background level, to the exemption levels for such long times that they are so long that we understand from science, from geology, let's say, that here on the surface and even in intermediate depths, change will occur, natural change that will disturb the materials there, and then they can cause some burdens to the future generations, not today, of course. And we must go, and this is now agreed internationally, that for high level waste, the only way is to go deep underground. The question is about 400, 500 meters and suitable geological formations, stable geological formation, such formations that we know from geology that these formations stay for millions of years and nothing there changed during these times. And with high confidence, we can calculate, model the behavior of the material there. And most of material will decompose. We will come, to these materials that we heard maybe about, in rock, glasses that are extremely durable. Even these materials during millions of years will grow. And a small portion of radionuclides will migrate through geological formation and achieve even biosphere. And through these models, we calculate that the results of this release of radionuclides will be absolutely negligible. So high level waste must go to deep geological disposal. So that's what agency recommends. So let's say it took me a little bit more than a half an hour. That was actually the core, the most important part, the message that I'm transferring to you on classification of radioactive waste. a little bit destruction now. So, you know, this is previous IA classification. And that's a little bit destruction for you because it's an example how we humans, we do from time to time mistakes. And sometimes are these even international mistakes, I'm sorry to say that, because they are humans. But for some of you who have biological background, they may know that through mistakes, this is the way of progress, by the way. So you know about mutations, yes? So through this, the biological species evolved, and through just one cell, now we are humans. And now we are developing artificial intelligence, right? So, related destruction, a previous IA classification. It was published in 1994, like that. You see that in the cover. Classification of radioactive waste. And what was this classification? It's in the table. It was, you see here, exempt waste, right? It's the same like today. So nothing changed. No radiological restriction, everything okay. Then it was a class which was called low intermediate level waste. And in this document, it was published, you see here, this is a copy-paste. Activity levels above clearance levels and heat output less than about 2 kilowatt per cubic meters. And that was a terrible mistake, which can cause even meltdown. If you have in a waste, which in the past it was called low intermediate level waste, and you will approach these 2 kilowatt per cubic meters, in a large tank with the waste, the temperature will rise due to the heat generation. And maybe you heard that in the past, in 1957, much before the Chernobyl, it was another big catastrophe in a place in Siberia, which is called Kishtin, when a tank with the waste, it was not called low-level waste, it was high-level waste, of course. But because of loss of cooling of this tank, so it was not anymore cooled, the water evaporated due to the heat generation, and then it exploded. And it was terrible thing, like Chernobyl. So, you know, if we would follow IA recommendation from this document, these things could happen even here in Europe, or I don't know, in the United States and so on. But of course, no one was approaching that. This statement was in the IA document. And the next slide will explain why I came to fighting to change this number. And nowadays, instead of 2 kilowatt per cubic meters, the document specifies the safety guide 1 recommends few watts, so 1,000 times less than it was 2 kilowatt per cubic meters. These numbers that I showed to you, 4,000 and 400, that's for short-lived waste, so nothing changed. Here, nothing changed. And again, 2 kilowatt per cubic meters for high level, but this is a border between low and low intermediate and high level. And you see here, GSG1 now, instead of 2 kilowatts, 2,000 watts, is just few watts per cubic meter. The point is, and this is a paper that I published some times ago in 2012, like, so we looked with my colleagues, and these two colleagues are from Russian Federation, Professor Polektov and Dr. Kasheyev. We looked on a possibility to use the self-disposal. What is self-disposal? You put in a container, let's say cobalt-60 sources or any kind of high-level waste, and because of self-heating, the temperature on this capsule will become so high that will melt everything around it and go down. And we propose to use these capsules in order to investigate the mantle of the Earth. So the capsule will gradually go down, 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 melting everything on its way until we reach the mantle, and we will go deeper. And using acoustic emission detectors, I had a project in University of Sheffield on that. We can detect what is there on the way of this capsule. So it will emit sounds, and this is a source of sound that goes through the Earth, and then all kinds of investigations. And here is a cartoon, because this is also a method of self-disposal, right? So you put the most hazardous waste in a capsule, put in a borehole, and then itself will go down, and this time it will go into the mantle, and then full story. And this is a cartoon that was about our paper. So you see here that it is just for fun that this self-thinking can go from Europe, let's say, to Australia. But this is, of course, just a cartoon, not a reality. So this number, so this is copy paste from the document. Nowadays it's changed. So instead of 2000 watt, it is just few watts. And perhaps it was a misprint or I don't know what, but I was fighting as an expert. I participated in meetings. I was writing letters to IAEA, trying to pay attention to correct this mistake. And the current version of the guide does not contain this terrible mistake. So maybe the message from this part of the lecture is that all the documents of IAEA that were superseded by the new versions need to be considered careful, because maybe some mistakes there were just corrected, and it's better always to use the newest versions of IAEA guidance, documents, and so on. In addition to classification of radioactive waste, we have got the categorization of the waste. So classification is the internationally agreed level that here, but from general industry, from general terminology, of course, that we categorize the waste in our documents by the point of origin. Where is coming from? Of course, we say that it's solid, liquid, or gas. We say that it's wet, maybe combustible, maybe liquids, compactable, and IAEA has even a document that recommends, again, not just terminology, but based on experience in the countries, about the categories of radioactive waste. Because when we are coming to the point of processing of the waste, then we need not just classification. So let's say intermediate level waste, but maybe it's liquid, it's solid, and high level waste again. So we need to know more than just the class. It's not enough to use just classification, but classification is something that is introduced in radioactive waste management as an important. So now the picture that was there is a very small square in why do we need classification. And this is the picture of nuclear fuel cycle. Maybe that you were already introduced it, no, but what is here? So we have the mining of the war. Then we have the enrichment, conversion, enrichment. We fabricate the fuel. We put the fuel in a nuclear reactor. We use it. After that, the used fuel goes here for storage. Then we have two options. The first one, it is open fuel cycle. So it goes after the storage to immobilization, the fuel. In Sweden and Finland, this is what they do. In the United States. So we put this fuel in some canisters, and finally we'll go to disposal in states in Yaka Mountain, in these European countries to their disposal sites. So it's open fuel cycle. So it's not a cycle. You see, it's just one through, say. But it's called nuclear fuel cycle. But there is another option which becomes more and more popular. And Russia is doing a lot in this area, by the way. Very progressive technology and so on and so on. So we can reprocess the fuel. So Russia is reprocessing the fuel. United Kingdom is also doing that. France is doing that. And after reprocessing, we can fabricate so-called MOX fuel. And because it's a lot of useful material, in the reactor burn, there's a small fraction of uranium. It is very useful material. And the point is that in nature, we have uranium ore so much that this technology is not much needed. It's maybe not economically very competitive. But nevertheless, it's a good technology to use. And if it will be used, then we have fuel for many thousands of years ahead, even accounting for the growth of civilization, industry, and so on and so on. So for fission reactors. So it's very small progress, very gradual. Almost nothing happens, but to the thermal nuclear reactors. But that's the question of future. And every time we hear that it's after 40 or 20 years, after 20 years, we will get an operating thermonuclear reactor. But there is a fun anecdote that this 20 years is a constant which does not depend on time. So after 20 years, they will say again the next step. In next 20 years, we will get this reactor operating. But this is anecdote. Maybe we will succeed once. Okay, so that's then here we have after reprocessing the higher level waste. And you see here appeared some abbreviations. So HLW, high level waste, intermediate level waste, low level waste, and so on. So now we understand at each stage of nuclear fuel cycle what kind of the waste is produced. And that makes them easy our consideration decisions, etc. Okay, so let me then go quicker. The norm containing waste. My next lecture is about norm containing waste. Actually, it's norm waste. So norms stands for naturally occurring radioactive materials. And I will repeat this, but pay attention that IAEA recommends to use, and this is done everywhere in the world, instead of 10 microsievert per year, 10 microsievert. 1 million means 1,000 microsievert per year, right? So it's 100 times higher for if the radionuclides is naturally occurring. Then instead of using this ultra conservative 10 microsievert, they use 1,000 microsievert per year. 1,000 microsievert as exemption for bulk amount of the material. So it's a big difference in approaches. And this is a normal because this one, it's very close to the background radiation, which is 2.4 millisievert per year on average on the Earth. Once again, in some places we got, in Finland, we got about 8 average per country. And you see how healthy are these Scandinavian people. And in different, in Cornwall, in the United Kingdom, so if you go there from my city of Sheffield, it's also a kind of mountain area. You also get some about 7, not 1, 7 microsievert per year, not 2.4 average per year, much higher. Nevertheless, the British are healthy and so on and so on. So this is a more reasonable criterion, but instead of it, in the clearance levels, everywhere it is used 10 microsievert per year. Okay, so but then I will repeat that and I will speak about in the next lecture. So let's meet in 5 minutes the example of classifications, just to again emphasize that not everything follows directly IAEA. Of course, the newcomers, the countries that started to use nuclear energy and to produce some waste and so on, they are using IAEA recommendations as they are. But the countries that started to develop nuclear sectors, so the United States, former Soviet Union, now countries of the former Soviet Union, they started to use their approach, and only this time they'll harmonize through IAEA. And this is a cover of a book. It's a book that I published with Professor Bindi from Imperial College and Professor Carol Janssen, former chairman of American Ceramic Society. It's an overview of radioactive waste management on the globe. So there are chapters on China, on European countries, on United Kingdom, all kind of these things, including classification. So that's for generic information if you want to go deeper. But from all the countries, the country that signed the joint convention with IAEA, and these are not 174 countries, member states, less countries, so about 60, 70, I can't remember exactly. They are reporting every year about the radioactive waste in their country, management of spent fuel. And then they must use IAEA because the IAEA is collecting information from all the countries. So inevitable, even using their system, they use IAEA classification. So that's the example of classification from France. You can see here how they, so it's a little bit similar to IAEA, but not 1-to-1. United States, it looks even very different. So now it's a trend in states to go closer to IAEA classification, but it's different. It's very different. United Kingdom, the classification looks very similar to that which is recommended by the IAEA. But in contrast with IAEA, where you can see some generic statements instead of exact statements. In United Kingdom, we have exact statements, exact numbers. You see these numbers that look similar. You see 4,000 here and 400 here, and some volumes and some concentrations as exact numbers. And that facilitates the war, because in generic term, then you need to add something to you and your country classification. So you can follow the UK classification because it's more exact. It's more exact than just the generic statements. Otherwise, generically looks similar to that which is recommended by the IAEA. The same situation, but without the exact numbers. It's in Germany. So I'm giving you just examples to judge about. Now you are in Moscow, in Russian Federation. The Russian Federation 2012 they published their classification, a very exact classification scheme. As a scientist, I prefer to use such type of classification. Everything here it's a numbers, it's exact. I can put a detector, and I can use intelligence, make automate everything. So based on these numbers, everything will be classified fantastically well by automatic system. Does not require to intervene, because everything is very well defined. So I prefer such type of schemes. Moreover, the Russia also are using the tentative classification. When you use a simplified approach, this is not real tentative. So you take a detector, you measure the radiation, and based on those or surface contamination, then again you judge this is low level, intermediate, or high level. After that, you go to this, you measure more exactly, and exactly you know what kind of waste you are dealing with. This slide is to explain that because of different approaches, the same material, which is one country is one, can be another country another. So here it's a long-lived waste from, for example, nuclear fuel components. So in Belgium, it will be called type B. In Finland, there is no reprocessing, they does not exist at all. In France, it will be long-lived intermediate waste. In Germany, it will be called non-heat generating waste. In Japan, you see here long-lived, low-heat, transuranic waste. And in States, you see here it's greater than class C. So that's the reality. But the common language everywhere is the IAEA classification that I just introduced to you. So this is the conclusion on this part, and we will maybe questions and then a small break. So the classification in reality are nationally based, but the conceptual scheme published in 2009 by IAEA serves as model everywhere. And it is based on activity level and half-life, and it is focused on likely disposal routes and points. But some countries continue to base their classification scheme on the simpler 1994 IAEA scheme. Please not forget that I just introduced you for your instruction this mistake that was there. So when somewhere in your country it is copied from that, if it is still there, 2 kilowatt per cubic meters, that is a terrible mistake. Be careful with that. Because if you make a big tank, maybe 10 cubic meters or 100 cubic meters, and if you approach 2 kilowatt per cubic meter, that's Chernobyl. That's for melting, that's Fukushima, that's Kristin. So it's not something that I want to distract. It's terrible mistake that never we should go to these threshold levels. So dear colleagues, with that I am finishing. I think that I shall stop my sharing, and maybe how Andrei, if you are still here, how you or my auditorium decide how you want to put some questions now, or we go to Norm and then we will speak.
Any questions?
Thank you, Professor. My question goes, if we have a short-lived but high-level radio waste, what would be the best strategy for such kind of?
I guess that it's still this so-called delay for decay, because even for high level, if it is short-lived, then you very easily can calculate the time that you need. And if it is short-lived, it's really short-lived. So it's short-lived, not, cesium-134, it is also short-lived, but the half-life is 2 years. Then it can be that you need if it is so radioactive that you need maybe 100 years to wait. Then you have to go not to delay for decay, right? So you need to calculate. But in most cases, if you calculate and the half-life will be not, but short-lived in many cases they are coming from medicine. And the half-lives in medicine are typically several hours, or can be even minutes, or days, In this case, you will not get 200 years in total to wait. And if the question to wait up to 1 year, that is easy to do. You put in a store together with other radioactive materials, and after years or maybe even 2, you open, you clear it, and that's it. That's the situation that you need to calculate. But in most cases, you will observe that everything goes easy. Just wait for the decay.
So that means we don't always take it to the disposal anyways. When
Absolutely. So that material after clearance will be considered as just a material. And from the point of view of radioactivity, it will be like a trash. And if some sanitary organizations also do not care enough, it is source of radiation source, then this is typically a capsule and material which chemically, biologically does not cause any harm. Radiologically is very dangerous. Radiation from there is very dangerous, right? So then after the decay of radionuclides and these radiations, it's faded, it's disappearing, then it's just trash. It's just a material to be thrown away. But thrown away doesn't mean thrown away. That means that regulatory authority will give you permission for clearance. So otherwise, in many countries, you'll go to jail. This is sounds simple, but the clearance is a procedure that must be followed because there are laws, and it's easy to say. But even if you work in a nuclear power plant, I noted to you that everything which is there inside initially is declared radioactive waste, and no one will allow you to throw it. It's then controlled. It is ensured that it's non-radioactive really, and only after that it goes with the simple trash.
Okay, thank you very much.
Hello. My question is for low-level waste, there is mentioned long-lived radionuclides, very low concentration, but not defined the limits.
Not define what? Levels.
For long-lived,
yeah.
At low-level waste.
For long-lived radioactive waste,
there
are generic recommendations, which sounds that 400 becquerel per gram average per the repository.
Okay.
Or in one package, 4,000 becquerel per gram. So you have a package which is, I don't know, 1 liter. And if you divide the total activity to this volume 1 liter, and if it is not higher than 4,000, then is eligible for near surface disposal following IAEA recommendation.
Okay. Thank you.
And in UK, this is the case. In UK, if you will take the table from my lecture, I will send the PDF files to Andrei and then he will distribute to you. But you can open, nowadays it's very easy. You open NDA website, you look to classification in the United Kingdom, and then you refer to the documents in the United Kingdom, and you have all kinds of the numbers. Now, but nevertheless, the lecture, of course, I will distribute to you.
Thank you, sir, for your lecture. I wanted to ask you about high activity waste. For that high activity waste, we need to collate. So I just wanted to know, there are like many variants of cooling system, like natural convection and also water cooling, the forced convection. And should we decrease the temperature of the waste, like our target temperature will be the melting point temperature, or like different temperature, which is like absolute minimum as much as possible?
For high level waste, the concentration of radionuclides is so high that they require both shielding and thermal generation becomes significant. So for shielding, you need shielding, that's it. For thermal generation, very much depends on the total volume. If you have just a small source, which is high level waste because the concentration is extremely high, radiation extremely high, you need a big shielding and so on. But it's just as one small by volume. Then the cooling, natural cooling, provides temperature, which is a little bit elevated, but it's still more or less acceptable, right? But if you collect a large volume of high-level waste, then in total, this volume produces so much heat. So if you speak about the tanks of high-level waste after the processing of spent fuel, the tanks, which are the volumes of tens of cubic meters, large tanks, they are continuously cooled, mixed and cooled. Because if you lose the cooling of them, they will start overheating. The water will evaporate and we can get in a big trouble. So then you must have cooling. So to answer to your questions, it is necessary to do shielding always if it is high level waste. But for cooling, you need to look on a elevation of temperature, which is dependent on the size, on the volume of this material. So in cases when the volume is small, then nature provides, look, another example. If you have canisters with vitrified radioactive waste, they are stored in dedicated repositories. They are shielded, of course, because radiation is extremely high. But the air is allowed to pass through these cylinders with the canisters and provides cooling of them. So it's not forced cooling. In a tank with the liquid radioactive waste, after the processing, I noted to you, these tanks are cooled and mixed. So like forcibly cooled in order to keep the temperature they're low. But these are for storage. And the storage in liquid form, it's relatively short. So everywhere nowadays, the high level waste after processing is vitrified, and then the glass is easy to deal with. So I hope you understand what is the correct reply, right?
Yes,
Shielding
I
always-
understood.
Cooling depends on the total volume. If it is small, the nature will provide, I mean, the air which is circulates there will provide no overheating. But if you collect together many high-level pieces, you will obtain a large volume, then cooling can be huge.
Thank you.
Thank you. Now we have 5 minutes break, and after that we continue.
Very good. I'll put here on the screen 5 minutes, and please come after 5 minutes. Or we can agree with you. So you come back in 5 minutes, right?
Yeah.
Okay, I will see the room and.
Mhm. Okay, please take your seats. We continue.
So, dear colleagues, shall I start the lecture?
Yes.
Okay, thank you. So, let's now speak about naturally occurring radioactive materials waste, normal waste. I am just returned from a conference that was held during 3 days this week in Saudi Arabia, in the King Fahd University of Petroleum and Minerals. It was on power engineering, but also many the people there were interested in the norm waste. And that was my second visit to Middle East country. So I was 3 years ago in an expert mission through IAEA in Kuwait. So you know these countries are producing oil exporting countries, and they are really dealing with this norm waste. I will show it to you. So many countries. Russian Federation, by the way, is also a big producer of the oil. So it's also a question that along with the nuclear sector, it's producing waste, and this waste is called norm waste. So the content of my lecture, I will introduce you what is the norm, and then I will go to the norm waste and the norm waste management, and also I will give you a couple of examples of the norm waste management. So the definition, concerning the definitions, for definitions, it's very good to take the available glossaries recently published by the IAEA. So in 2019, it was published a glossary on the terms used in the nuclear sector. And last year, they published, the cover. It's given here. It's about the terminology used in dealing with the radioactive materials, nuclear materials, all kind of the definitions, including many that you can find in papers and so on and so on. So it's good for understanding each other. As for the norm is naturally occurring radioactive materials. So by definition, norm is a radioactive material containing no significant amount of radionuclides other than naturally occurring radionuclides. So you take something from everywhere, from the nature, from a plant, from a room, from even a nuclear power plant, from everywhere you like. And if in the material there is no significant amount of other radionuclides than naturally occurring, you say this is norm waste. This is norm waste. The point is that the exact definition of significant amount, it's not recommended from somewhere. It's a question of regulatory decision in the country. So in a certain country, you can have one level. If you go to another, you can find another level. So as for norm, you understand what is norm. So I will use, this abbreviation. So naturally occurring radioactive material. And this schematic shows to you that it's a natural component of the earth. It is everywhere. It's in our body. I noted to you already carbon-14, right? But we also have some tritium in our bodies, and it's not coming from nuclear power plants. It's coming from a source which is called cosmogenic, because our Earth is irradiated from cosmic space by highly energetic particles. All kind of radiation is coming from the space. It's bombarding the atmosphere. By the way, it's producing in the atmosphere muons. The muons are like heavy electrons. And these muons are passing through us in large amounts. And if we have a muon detector, we can, find some muon shadows. It takes a long time to do that, of course, but there is nowadays even kind of one technique to identify what is inside of a pyramid in Egypt, or to look what is in a reactor, maybe even Fukushima, and other objects, and so on. So we have cosmogenic norm, naturally occurring materials, and we have other type of radionuclides. These are so-called primordial. What is primordial? Perhaps you heard, now this becomes more and more interesting issue about the evolution of universe. There is a theory of Big Bang, and is recognized everywhere that initially the universe was very, very compact and was extremely radioactive, of course. And 4.5 billions, not millions years ago, when the solar system was formed, the content of some long-lived radionuclides was not like today. It was much, much more uranium-235 on the Earth. It was so much about 2 billion years ago that in Gabon, in Africa, there were operating nuclear reactors without any engineering. It was by nature. They operated for thousands of years there. The naturally occurring nuclear reactors. So the uranium-235 was birthed in addition to the decay there. Because the enrichment at that time, it was not real enrichment, it was natural content of uranium-235. It was so high like today in the reactors, even higher. So these are primordial. So these are continuously created due to the bombardment of Earth, atmosphere and Earth by radiation from cosmic space. And these are decaying remnants from the Big Bang finally. But in reality, it was a supernova that exploded, and then the materials from the explosion of supernova, because supernova is creating all kind of heavy radionuclides, all kind, including this uranium isotopes and thorium and all other, right? So these are tables. This is the main norm, radionuclides that occur in nature as the nature was created. The religious people say by God, but the scientists after the Big Bang and so on, explosion. So you see here our uranium-238, half-life in billions years, right? Uranium-235, thorium, potassium-40. It's a lot of potassium-40. That's why we are radioactive. The walls are radioactive. That is why exists a so-called banana principle. So how many bananas we are eating to receive the same radiation, like from medical treatment, or maybe from a flight, or maybe from working for a nuclear power plants and so on, because a lot of potassium is in banana that we need, of course, potassium, but among it, it's this fraction of potassium is potassium-40, and it decays. And then you see here atoms, some of them are really extremely long-lived, you see. So samarium-147, it's very, very long-lived. Lutetium-176, very, very long-lived, and a large fraction of these are radioactive. In total, the amount is small, of course. So there is no significant radiation from this material. But from potassium-40, it's typical radiation that comes from the walls. And if you work in a sensitive laboratory, you need to shield somehow, you know, your detector from potassium-40 radiation. So these are primordial. They are still decaying. They still decay. And these are characteristic of some cosmogeneous. They are also norm. So carbon-14, it is formed there in the atmosphere. Tritium that we care about it. It's quite short-lived. You see here 12.3 years only. This is a long-lived carbon-14. Because of that, we are using this dating. And you see, so there are many. Not I took just several of them as a demonstration. So these are decaying, naturally occurring radionuclides that exist in the nature. And as for uranium, thorium, then we have plutonium, let's say, we have these three decaying series. So if you start with uranium-238, it does not go immediately to a stable radionuclide. It is on the way of its decay. It's creating many, including gaseous elements like radon gas. If you live in a basement, you are breathing radon, radioactive, which arises from the decay of uranium, which is in the rocks everywhere. So it's uranium series, thorium series, and this is called actinium series. It's by definition in such a way. Important is that the final decay radionuclide, it's not radionuclide, it's lead. But the different isotopes of lead, they are stable. So after uranium-238, we get lead-206. 208 after the thorium series, and 207 after actinium in the decay series. That's about you see it should be called uranium as well, but since uranium is already here taken, because of that it was decided to call the series, because here the longest is uranium-235. This is the longest in this series. And if you find here the lead-207, we can identify that in the past it was a lot of uranium-235, and in such a way, looking to the ratio of lead, we can identify what was at the beginning in the ore and the material and so on and so on. So let's move to our norm waste. So when we speak about norm, so we already know the definition. So norm is radioactive material containing no significant amount of radionuclide other than naturally occurring radionuclides. So potassium-40 is okay, uranium-238 is okay, and the radionuclides in decay series of this series that I just demonstrated to you, it's okay. But if you have some, I don't know, zirconium, some aluminum, some sodium, some cesium-135, a lot of 137 cesium you can find in the nature. Where is coming from? Because it cannot be norm. It is not created by radiation. It is not a remnant because the half-life is just 8 years. This is the result of testing of nuclear bombs, colleagues. So many bombs were tested in the atmosphere and they contaminated the earth, and we have cesium-137 in the environment. And it's coming from the strontium-90 and so on. So it's not okay. This is not norm. That's norm, right? Now we go norm procedure. So we have a process. We are using somewhere the materials because we are taking material from the nature to construct something and so on. And we have some procedure. Remains from a process, so contaminated by naturally occurring radioactive materials. But colleagues, this is still not norm waste. No, this is still not norm waste. So be careful, particularly if in the room there are people who work for regulatory authorities, maybe even highly administrative persons and so on and so on. Don't be in a hurry to declare that this is waste, because then the story becomes very complicated and very expensive and so on. You need to work properly with the radioactive waste. So norm waste is naturally occurring radioactive material for which no further use is foreseen. And it's still, maybe but it's norm waste. This is norm waste. So if the material is residue, but maybe will be used somewhere, it's still fine. If it is not declared as radioactive waste, norm waste, then it's better to deal with. If it is here, all the regulation from regulatory authority come in place. So norm residue may or may be not waste. So that's what source is taken here. And the picture is shown to understand. So we have natural sources, we have here norm, we have norm residue, and then we can have a small portion of this material as norm waste. And this is time to recall what is the radioactive waste that we must do to have radioactive waste management and maybe norm waste management. So the definition was given in the previous lecture, and you remember that I informed you about the clearance levels that were obtained on the basis of 10 microsievert per year. So it's this slide. I demonstrated it to you, right? But this document, this basic safety standard, stipulates that for low probability scenario, there is a different criterion that can be used. And instead of 10, 1,000. So 1 milli means 1,000 microsievert in a year. And again, this basic safety standard stipulates that for radionuclides of natural origin, those that existed or are created by cosmogenic radiation, cosmogenic radionuclide by cosmic radiation, they are allowed to be exempt based on levels that are obtained by using the dose criterion of 1 millisievert a year. 100 times higher, larger compared with all other artificial radionuclides, man-made, let's say, radionuclides. This cesium-137 or strontium-90. For cesium and strontium, we use 10 microsievert per year. For norm, like potassium-40, we use 1 millisievert per year, 100 times higher level for clearance, which sounds reasonable because this is compared with background radiation. So you see here, these are copy-paste text from the basic safety standard, and the question here is about the typical activity concentration with 1 becquerel per gram. And in the chain, you see here the question for potassium-40 is the question about 10 becquerel per gram. So these are reasonable level for clearance and exemption that are used, but they are calculated for each radionuclide and are recommended by IAEA in basic safety standards. There is so-called schedules or tables, 1 and 2, and for all radionuclides there, all of them, these numbers are certainly given, explicit given for each of them. You can take from there, and then most of countries they use as they are, but not all of the countries, because in some countries the background is different from ours. So it's not mandatory to use very conservative numbers from IAEA. They can be higher because the harm is not real. So that's again just a repetition. That is the definition of what is what. So when we speak about the waste, it's a question about regulatory and legal aspects, right? And the clearance levels and the waste, it is here. The waste, it is here. So we have norm residues that may be even reused. There is not real hazard from them, high hazard from them. But there is also some of the material is declared as a norm waste, and then you have to go into the radioactive or nuclear waste management area of activities. So norm waste. So this is naturally occurring radioactive material, norm for which no further use is foreseen. This is norm waste. And they are arising from many processes that deal with natural materials, mainly in the mining, but not on and processing as well. So here are examples where the norm waste is produced. So mineral mining and ore beneficial is producing huge amounts of norm waste, huge amounts of materials that contain norm, and they are not needed, these materials. So residual, but then they are declared, if they are not needed, they are not used anywhere, they are declared as the norm waste. Oil and gas production is producing a lot of them. Geothermal, it's a kind of renewable energy, and it's also producing norm waste. Metal, and example, it's uranium for reactors, right, for use production. So, but not only, so processing of metals, it's producing. When we burn coal in power plants, we are burning thousands of tons of coal. Then again, thousands, even millions of tons of ash is produced. And by the way, this first of all, in the atmosphere, it is released not just CO2. Unfortunately, even radioactive elements are discharged by the power plants that are burning coal. Even I'm not abusing and not here the tables of that, but there are data on the emission from the coal burning plants of radioactivity and radionuclides, and they do that in a higher concentration than the nuclear power plants, by the way. So, but look to these numbers that are here. They are provided by Professor Sapochnikov from Moscow State University. So look to this number that about 550 million tons of uranium are in the dumps after the burning of the coal. 50 million tons of uranium, not tons of the ash, tons of uranium. And you can compare with the amount of uranium which is inside of reactors operating nowadays. And these numbers is not 50 million tons. It is just 0.1 million tons. So it's 500 times more uranium in the ashes, which stay in the environment everywhere around the coal burning plants. There's uranium there. It's norm. Because of that, it's not the same attitude like for the uranium, which is nuclear power plants and all kinds of radionuclides there. But it's 500 times more uranium in these residues. after the burning of the coal. So pay attention. So here the numbers, you know, it's of the states you see here. So it's huge amounts of the material produced when they burn the coal. Water treatment is also producing residues that contain, and then we got norm waste. Sewage plants, fertilizers, when we extract phosphate, typically fertilizers. As a part of it, we got uranium and thorium as a component, which is not. And that's a little bit for destruction maybe. So the first one is taken from I worked for 8 years in Vienna, in Austria, as a staff member of International Atomic Energy Agency. So in Vienna there is a very interesting museum of technological museum of Vienna, and among other objects that are exhibited there, I took a photograph of a toothpaste that was radioactive, because long time ago, you see here that's Berlin here noted and so on. It was thought that radioactivity is very good for the health, and that was recommended, you know. So it's sun cream, you know, this is in German language everywhere. So it was considered that if you brush with a little radium here, our brushes, we feel much better and so on. And I have some terrible photographs that is better not to show to you, you know, what happened with the people that abused the use of radium actually containing water. This is in Russian. Most of you understand the Russian language, and you see here that that was everywhere in the world, not just in Germany, in Austria, in Russia. So that was former Soviet Union at that time. It was in States. It was everywhere. It was considered that consumption of actually norm containing materials, water with radium and so on, was very healthy, and indeed some patients felt better for a certain time, but only for a certain time after the use of this radioactivity, their view and so on. So cancer typically, so, and terrible lethal doses they obtained after using these things. So we learned through life that radioactivity in high content, it's very, very dangerous. So this is about the content of radionuclides in norm. So maybe just so you see here about the content of sludges, let's say, of radium. Mainly radium here is reported. So in phosphate, I noted to you here, phosphogypsum and so on. So very, very high content of radioactivity. It is there, very high. So we should care about even radiation. So if you look to the classification, you already understand what classification. So here is the scheme that was in previous lecture. So waste and disposal route of the waste, and the norm. It's here because typically this is long-lived radionuclides. So they are not short-lived. You see, they are in half-life in this part. Like this, the uranium, very long, and thorium, very long half-lives. And but they are unable to very low level waste landfill disposal. But some of them can get even, you know, catching a small part if the concentration is really very, very high. Even be considered as intermediate level waste, and they cannot be accepted to near surface disposal even. But most of them are going to this part. So it depends also very much on the volume. So it's not a uniform approach to norm everywhere. If you are in a country where you have, you know, 1 cubic meter of the norm, that's an easy to take story. But if you have these millions of the tons, that's absolutely different story. From one side, we simply cannot afford. Applying to the norm waste the same principle as we do for nuclear industry. Instead of that, in nuclear industry, and instead of that, it is double standard, colleagues. Really, it's a double standard that is internationally recognized. So for the nuclear industry, we have this 10 microsievert per year as a level dose limit for clearance and so on, which is 100 times more conservative compared with norm, at least 100 times. So it means that we are ultra conservative, and it means that we for the waste that arises from nuclear industry, we are pumping there a lot of resources. And In many cases, this is not really justified. It should be more reasonable. But at the moment, this is the situation. But for norm, we are using this 1,000 microsievert per year, 100 times larger, which is more reasonable to is commensurable with the hazard that comes from this waste. And let's go. So waste streams generated during the different phases of mining process. We got exploration waste. So when we are trying to find something, we are producing some piles of materials. And they contain normally because we are taking them from underground, from where is the ore and so on. Then mining waste, tailings, they are most problematic. They do huge amounts. In situ leach waste, so you know this leaching process when they extract uranium, so then a part of material it is then goes to the beneficiation plants, to enrichments and so on, processing, but a part is left as residue, and it's still containing a lot of decaying radium more, and all kind of processing wastes. So these are really mountains. And tailing. Typically 5 to 10% of target metal and other radionuclides remain in the tailings. I forgot whether it is or not in the list of participants anyone from Uzbekistan. But in Uzbekistan, there are still very good ores containing a lot of uranium. And there's so much uranium that after processing, these 5-10% in other countries would be still considered as good to further taken and to process them again. Because very large amount. Uzbekistan and Tajikistan seems to be also the Tajikistan is the case. Is anyone from Tajikistan? You can inquire, look to the publications in this area, or maybe some of you are even aware about the tailings after the extraction of uranium, and some of them contain so much uranium that another country would be considered amenable to take them into process further. But in Tajikistan, it is residual, let's say. Maybe it's not declared as the waste. It's residual, normal residual. Radium-226 is very typically there. And it's not, radium-226 is not just the question that it produces radiation, but it also, because it's decaying, it's long-lived radionuclide, but it produces radon, which is a short-lived decaying gaseous radionuclides. Then we can breathe it. It is absorbed very well by the hairs, by the skin, by everything which contains a little grease. And unfortunately, it can stay in the lung, and then if it is much, can even cause some health problems. Radium-222. In oil and gas production, so we are extracting the oil from deep underground, some well, there is a well here, and we got some pipes there. And here on the ground, we got these are decay products of uranium, so radium itself, decay product of thorium, and then the gas radon, it's partly dissolved in the water, and then this water from underground, it comes out. So then we have on the internal parts of the pipes these scales, so some precipitates, typically these are sulfates, barium sulfates, but also includes radium sulfates and radium-226. So this radium is then in a higher concentration than it was in the initial liquid here, because it settled on the walls of the pipes, and it decays and it goes through the whole system here, and then we got in the water. You see here the radium that maybe was dissolved, particulates, some hydrosols that are there in the wall here in condensate, maybe some aerosols, let's say, that also in the gaseous phase containing at least radon that is absorbed from these particles, and the gas as well. So in the natural gas, which is pumped through the pipes far away from the point where it's extracted, let's say from Russia, it's pumping through to many countries the gas. Initially, the content of radon-222 is, but through its way, it's decaying. So the concern when we are burning the gas in Europe and so on, and other countries and so on, it's already practically no radon. On its way, it's 3.8 days only the half-life. So through long way to come to consumer, it's decaying. I put here the cover of a good report about the guidelines for the management of naturally occurring radioactive materials in the oil and gas industry. So this is really published in 2008, but it's not an obsolete document and so on. It is good because I noted to you, I was in Kuwait and as expert to a meeting on a workshop, regional workshop, how to deal with the north. This is a question of the countries, these producers of the oil and gas that are selling, because they sell the oil, they sell the gas, but the waste is there. And these are, again, filled with this norm waste. And it's a lot of radon generated there, it's a lot of radium generated there, and in many cases, this is the big question and so on. I had in Sheffield a PhD student that had a project on these scales. So I'm familiar with these systems. So oil and gas. So we have these produced waters where we have 10 times more water than so it's a lot of production. You see here per barrel of oil, we got 10 barrels of produced water. The water is used, to extract, to wash from down there, and is circulating, but a lot of water, produced water, remains as the waste. And then we need to do something with it. Then we got these scales, and again, some numbers are given here. Approximately 100 tons of scale per oil well are generated in the United States. And this is a typical figure that can be considered as a similar in everywhere in oil and gas industry. And we got also the sludge that in drilling, these boreholes, they are filled with the mixture of clay and water that keeps everything during the drilling and so on and so on. So a lot of this norm sludge is produced everywhere, and again, these are fields where we have large amounts of norm waste. So this is a photograph to show you how looks a pipe. You see the scales inside of this pipe. So during the operation, passing through this pipe of, let's say, of the oil, the scales, so sediments were poured from the internal part. The pipe becomes a little bit narrower and so on. After its usage, it's radioactive. And you see here the reported content of radionuclides. You see here for an becquerel per grams, and this is a short-lived, let's say, version of the lead. And it's producing radiation, and the levels can be high. But you see here that the content in becquerel per gram can be quite high. So radium up to 400 becquerel per gram. This is a really high concentration of radium in the scale. So it's not something that can be tolerated negative. So if you look to the operators that work in oil and gas industry, then they have two types of a danger from a norm and radiation, because these scales are inside. But when the radionuclides decay, the radiation passes through the walls of the pipes, and there is significant gamma radiation. Seems to me that I have a table with the levels. Anyway, in the report, these levels are provided. So the levels are even higher than can be even higher than for operators of nuclear facilities in oil and gas industry due to the norm. And also they are opening, they are closing, opening different flanges, different changing pipes, and so on and so on. And then these norm materials are in addition to irradiation, then we have alpha, typically the normal alpha decay radionuclides. And alpha is very dangerous from the point of view. So if it comes inside of the body, then the effect of this radiation is much higher. So this is considered. And yes, this is the table that, yes, it's about the radiation levels and microsievert, but look, this is not per year. This 10 and 1000 was per year. This is per hour, not per year. So this 300 is just 1 hour. So in crude oil processing, you see here quite high level, right? In different parts. In associated, you see white level. So you see here in natural gas pumping, so 200 microsievert not per year, per hour. So in a 50 hours, you are to this level that it is there in regulatory documents. So they are even from the point of view of irradiation. But again, concentration in the previous slide was right. The very high hazard, masks and so on, to not breathe these materials inside, to not consume it with the water, with the hands that are contaminated, with everything that is contaminated around. So norm waste can, from the point of view of radioactivity, really dangerous. Typically, the content, so this is taken from an IAEA publication, from the technical document on norm waste management recommendations, practices that are everywhere. So this is a typical 1 to 10 becquerel per gram is this clearance or exemption level. So if it is less than 10 within this interval, these materials are really genetically safe. So you see, this is the soil. This is things that no one questions. So we are growing plants and so on. And we are not scared that somehow this is radioactive. Also, again, everything around us is a little radioactive, right? So the clearance of things that are out of radiological control are in this part of the plot. But the line is shown here in bold. So you see here non-optimized or regulatory resources. So not use of regulatory resources. Yeah. And here you need a kind of optimization after 1 is considered, but even higher than really. So these you see here, the phosphate, bauxite, rutile, some of you see minerals like so if you go to zircon, then it can contain uranium-238. So this is silicate of zircon, a very, very durable mineral, and in some cases it contains radioactive uranium or thorium. And in many cases there are some sands containing zircon, and the radioactivity in these cases is higher. But as for the uranium to be extracted from there, is almost impossible. It's extremely durable mineral. And moreover, typically the content is less than 10. So it's not really of hazard. But look, pyrochlore, monazite, very typical mineral containing a lot of uranium, or thorium in many cases. Uranium ores are here. The content is very high. So that needs to have use of regulatory resources and to limit contact with these minerals that are shown here, like these monazites. So in many places, monazite can be observed even near the surface. And then the radiation is very high to the decay of thorium, typically thorium. And in principle, yes, in form of small particles and so on, can even enter into the body. So we are coming to the norm waste management. Again, we have here administrative activities. And maybe in this part to emphasize to you that please be aware again that instead of 10 microsievert per year, it is used 1,000 microsievert per year. And the exemption clearance levels are much higher for norm compared with non-norm materials. In administrative, all the documentation should account that norm is different story compared with artificial radionuclides. As for the management scheme, it's genetically same. So we need to apply some predisposal. Predisposal means we prepare the material for disposal. In certain cases, and this is true particularly for the norm, not much predisposal is used, and we can organize disposal. If, let's say, the mine that was used to extract the material is still available there, then maybe this tailing can be put back there, and this is disposal. But in some cases, we need to apply many things. These waters, maybe we need to process them, to pretreat them, then to purify this water, to reduce the volume, to reduce the volume to remnant materials which are very ready to immobilize somewhere, and so on. So for different parts can be different stories, not one for everyone and everything. And then we deal with radioactive materials, the generic scheme is that was shown here. So if the material is needed, this is not waste, is not, let's say, my lecture. This is my lecture here. So unneeded material, waste material, maybe we can clear. So you look to the clearance levels, and if your norm, it is still okay with this 1 to 10 becquerel per gram, you can clear it and allow to industry, to anyone to use it. Maybe not now, maybe in the future they will say it's a lot of waste, why not to use it? So if it is below the clearance levels, it means it's safe. It's safe to be used everywhere, anyhow. That's the clearance level. And then authorized discharge that goes for liquids, for gases, and regulated disposal if these two options are not available. And then we have a quite complex system of radioactive waste management, and we have a life cycle. So this should be considered, separately. And so we have this. Again, you see here, this is a clearance if possible. If not, we need to do everywhere characterization. Then we go to the treatment. Then we go to the conditioning. Then we prepare a package. So conditioning produces packages. Then they can be stored, they should be transported, and then they finally get to a near surface repository or deep underground repository if we are lucky and we are under you see here the storage for the decay. Then we maybe discharge it because it's waste. Because of that, I mean to put it to the environment, and depending on the physical form. So that's the easy case. In many cases, possible. For the norm waste, this is from this report from oil and gas industry. I will not go here. I don't have time for that. But as for TechDoc, you see here norm waste, very different stories. If it is a large volume, if it is a medium volume, and if it is small volume. So if you are with a small volume, don't complicate the life, and understand that there are possible options when you can a little bit disperse. So mix with something which is not containing, and then you get under the clearance level, and then the problem is solved. And this is an option for small volume waste. But every time this is sorted case by case. So in a management, there is a document, there is a handbook published by IAEA in 2017. I was the technical officer of IAEA who collected these experts. They did this handbook on the selection of technical solutions for the management of radioactive waste, including norm. So there are phase approach, evaluation, selection of optimum norm waste management option, and then implementation of the optimum norm waste management. Is not one the same everywhere. We have, like in previous slide, large volumes, medium volumes, small volumes of the norm waste. Of course, that even for countries which are not nuclear countries, they do not use, maybe not use even research reactors. So they got just norm waste, only nature occurring materials. Maybe some misuse sealed radioactive sources, but not much other. Nevertheless, should be a national policy and strategy. National policy and strategy. A good guidance document published by IAEA in 2014, seems to be a little later. You see policy and strategies for radioactive waste management. If you work in a regulatory organization, download it and use it. It's very good to prepare all kinds of documents and then to care on what and what and what. So that's a very good guidance. It explains the responsibilities. The real final responsibility is to operator. It's responsible for all safety-related issues, but everything, rule, criteria, guidance, licensing system, and so on goes to regulatory bodies, and they should work in harmony. Each of these two bodies do their work, and if they communicate to each other, then the final target always will be achieved. The IAEA, in principle, supports very much reuse when possible. And there are even in European Union some directive of that, of Euratom. I put here the link. So when possible, when the content of norm radionuclides is not going much higher than 10 becquerel per gram, in many cases, the materials that contain norm at such concentrations can be safely reused, and this is encouraged always when it's possible. Everything should be assessed, and if you are with the high relative not high concentrations, so below 1 becquerel per gram, maybe exceeding 1, but not going very high, than 1 becquerel per gram, then this material can be safely reused. Of course, that after it should be a post-closure phase, when particularly in the cases when we have large amounts of norm. Then you see here the points of the sites, knowledge about the sites, about the closure, monitoring, active control, passive control, all these issues are, so the records and so on are taken into account. And let me go very briefly about 5 minutes because I'm exceeding my time. So these are examples of norm waste management. So in mining operations, we got waste rock typically, and this rock typically may remain in place in piles because what is a rock? It's a solid material where the material is quite well, like I noted, zircon. So silicate and zircon. It's an extremely durable material. And nuclear industry are trying to synthesize zircon in order to immobilize, actinize long heat and so on, because it's very, very durable, very good material. Tailings from the dry separation of heavy minerals, usually mixed with other low activity residues, return to the mining void from where the material was extracted and covered with non-radioactive sand or overburden. So this is experience in the countries. For bauxite tailings, so usually disposed as a slurry, contains 10 to 30% of solid. Typically, this is the water slurry in large engineered containments, and they are lined with the clay because it's low permeability. Can be also additional polymeric material. Tailing and phosphate gypsum from phosphate fertilizer production usually return to the mining voids as a slurry again. This is a photograph that shows surface ring dike in Pondvents in Australia. So you know Australia, it's a large producer like Canada, let's say, of uranium ore, and then the places where it was extracted. So we see large ponds that contain the slurries is the residues after the production of uranium. Scale deposits, the main option after removal, burial at the site that will remain under institutional control because radium-226, which is that's the main radionuclides there, it takes very, very long time. So, but at least nowadays, this is the practice that is used. Of course, that can be disposed at Hradov waste disposal facility if it is that the possibility. There is a developed radioactive waste management system, and moreover, low intermediate level radioactive waste disposal facility. So that would be a preferred if available. So you see, this is under the control. This is the intention that in the future will go to such situation. That is the case of these scales. They contain radium-226. Sediments and sludge, they need in many cases to be treated. So then we need some treatment facilities like to purify the sludge, to concentrate further. For the dust, we see here disposal as industrial waste in a controlled landfill facility. Liquid norm waste typically, so aqueous streams, if they cannot be recycled, so maybe several times are recycled, but not anymore, generally treated to remove contaminants, and then these contaminants that removed need to go through all these things that I explained to you. So these are the conclusions on norm. So the conclusions are this, the definition to recall what is that about. So the point is that there are the naturally occurring radionuclides in the content of other radionuclides, let's say man-made, like I noted in cesium-137, is not significant. And since in the nature we have already some strontium-190, we cannot put zero there. We cannot put zero there because already we have in nature man-made radionuclides. Not your small country produced these radionuclides. They were produced during the tests of the bombs of nuclear powers, of States, Soviet Union, China, France, British, of course, tested the bombs until they did not to do that anymore. And we have to have some significant level indicated for the norm that it is allowed, even for man-made radionuclides, to be considered as non-significant. So norm waste, norm which no further use is foreseen, and the key issues are typically large volumes. So it's a problem when the volume is large. So this large piles of ashes after the burning of the coal and mining waste and so on. Disposal costs are high. They are never cheap to dispose. Even near surface is not cheap to do. So resources. And when you go to very high volumes, then resources are very high. Long-lived radionuclides complicate very much everything. Very much everything. If the content is very high by concentration, we need to go into underground, and then we have exponential growth of the cost. We go for 1 cubic meter, we need to pay 100,000 of euro per cubic meter. So that's something unaffordable. And limited containment in many cases because of, again, maybe linked to the large volume of the waste. So dear students, participants, many thanks. That's all that I wanted to give you. I apologize a little bit. I went out of schedule, but yeah, what to do? So maybe some questions you have to me on these things.
Thank you very much. Yeah, any questions? No? No, okay. Thank you. Thank you, Michael.
Okay, thank you. See you again.
So we have a lunch. Yeah, please take your little piece of
Это должно быть.
Видно меня? Hello, dear colleagues. I was here at 3, but you wasn't. I hope the lunch was good and you have a new force to prolong our school. First of all, we will discuss our strong deuterium separation practice. And I just want you to show exactly, we will repeat the steps. As you remember, from the first initial solution, we took only 1 milliliter of this solution for separation. And that's why the strontium and yttrium activity should be half of the initial activity. And after that, we add TBP and shaked, and in organic phase went yttrium 90, and in the acid phase stayed strontium 90. And the activity should be 30,000 CPM per each radionuclide. After that, we re-extract yttrium to water solution, and strontium we just dilute with water, add some scintillator cocktail, and measure total of strontium 30,000 CPM. But sorry. We took total of yttrium, but 0.5 milliliters of strontium, because the acid was concentrated, and to dilute it well in scintillator cocktail, we should achieve the pH around 7, neutral pH, and that's why we took only half of this solution for measurement. We used scintillator counter tricarb for measurements. And what we found, what we took. As you understand, I hope the efficiency of strontium measurement is 100%. But for yttrium, because we measured it using Cherenkov counting, direct in the water, that's why the efficiency was 50%. And I calculated all the numbers according to these steps, that here we took 1 milliliter. That means that the strontium and yttrium should be 30,000. And here we took half, and strontium should be 15,000. And according to efficiency as well. And what we saw? We saw the separation coefficient. It is the most important part of the task. And we see that the zero group was the best. I'm not a wizard. Really, it is not because I was the supervisor of that group, but really the separation coefficient was about 49% and 51%. And for other groups, it was different. The worst, I think, for the first group, AK, 79% for strontium and 21% for yttrium. These is quite good. That this one is not also very good. But the next step was to remeasure the samples and to see how after separation, you see after separation, this fraction with strontium, the activity of this fraction should increase because yttrium will accumulate here. And the activity of yttrium fraction should decrease because no parent radionuclide inside. And we should see only the yttrium decay. And what we see? This is the first point, the second point. And this is for strontium. The numbers is the numbers of the group. And for strontium, the activity should increase. And it works for 3 group, 2, 4, and 5, a little bit. But for example, for the first group, you see that strontium in the second point fell down. And that is not good. And for the third group also, strontium fell down. And results for yttrium. For yttrium fraction, the activity should decrease. And it works well for the second group and for the fourth group. But for other groups, it doesn't work. We will continue this experiment, and I will show you how it's going on. But what we can see? We can see that the separation is not a very easy process. We can see, according to the results, I will show you maybe later that the quality of solution became very bad, and sometimes the solution colored because of some organic leaves there. And that means that the separation process wasn't clean, wasn't good quality. And results here can be considered to that quencher effect. Maybe on lectures you heard about that quencher effect that can be chemical quencher and optical quencher. But I can say here that for the first group, the quencher effect was very, very high, and that's why we see so small number for the second point for strontium and for the third group as well. But the competition is continuing for groups 2, 4, and 5, and we will see the winner in the end of our school. What I want to say, that the looks like very easy task can be really difficult in practice. And I think for these results, for good separation coefficient, the group where I was a supervisor, that group was the chemist students, and maybe they had some skills for separation process. It looks very easy, but it is difficult. You should be very careful to do this procedure. Okay, if you have any questions, we can discuss today or later. I will inform you about results next week. And now I want you to tell about environmental monitoring and how it works here in Russia and in Europe. Maybe some of you have connection with the environmental monitoring, maybe not. But I hope that it will be interesting for you. Man-made radionuclide sources in the environment. As you understand, now we are living in epoch when the artificial radionuclides became the part of the environment. And if, for example, in the end of 20th century, the 1 becquerel of plutonium, for example, in the environment can be estimated as a contaminator or contamination, nowadays 1 becquerel of plutonium is background level. Everything, everywhere has some artificial radionuclides, contains some artificial radionuclides. And that's why it is very important to control how this background increased or decreased in the environment. And of course, the environmental monitoring consider not only artificial radionuclides, but also for natural radionuclides. But according to artificial radionuclides, the main sources of man-made radionuclides released in the environment include previous nuclear tests in the atmosphere and activities radiochemical plants for spent nuclear fuel. And nowadays, the radionuclides continue flowing to the environment in the La Hague, or for example, in France, in the Sellafield, England, in Russia, in some enterprises, and in China, nuclear power plants, for example, to the Pacific Ocean, they flows a lot of radionuclides. But here you see the scheme, how many radionuclides went to the environment during some accidents. Monitoring around nuclear facilities. This is a simple scheme, how it works. Radiation monitoring involves the measurements of radiation dose or radionuclide contamination for reasons related to the assessment of control of exposure to radiation or radioactive substances and the interpretation of the results. And the system of integrated dynamic surveillance. And usually it should be one center to control all these parameters together. And nowadays, this task is not very hard and complicated because of artificial intelligence. And everywhere in the world, and of course, firstly in Japan, around nuclear power plants in Japan, the artificial and natural radionuclides controlled by artificial intelligence, AI. Program usually contains on routine monitoring, emergency monitoring, and the objectives you can see here. The objective of routine monitoring is compliance with safety standards and long-term trends, control of accumulation in environment, and control air, soil, water, foodstuff, and other. And also we should note and should be it is important to control incidents, emergency monitoring. It contains on accessing radiological situation and possible consequences, support of countermeasurements, and of course we should measure air and vehicle-based dose rate, and mapping air, soil, water, and food stuff. Typical required lower limits of detection for gamma-emitted radionuclides and the condition of normal operation, emergency situation complied. And it is very important for you to understand that every enterprise, including nuclear power plants, flows radionuclides. And of course, everything depends on the number of that radionuclides. But if we say that nuclear power plant doesn't affect the environment, it's not true. It affects the environment. For you as a professional persons, you should understand that it only depends on numbers. And tritium, for example, and carbon is ongoing from nuclear power plants to the environment every day and every hour. Here you can see the nuclear power plants in the world. And you can see some concentrations of nuclear power plants, yes? And the territories without any nuclear power plants. And for example, in Russia, we have only 10 nuclear power plants for so big territory. And compared to England or France or Japan, we have no nuclear power plants at all, I think. And these territories should be on monitoring firstly, because these territories are the most potentially dangerous. But nowadays, scientists think that it is impossible to happen something like Fukushima or Chernobyl. It is impossible technically, because the experience of these two accidents gave to people a lot of knowledges how to control these stations. But for the environmental monitoring, these areas should be controlled more attention, with more attention. The most important radionuclides that should be controlled during the nuclear power plants operating, of course, inert or noble gases, tritium, carbon, and others. Why it is very important? It is very important because the small increasing of concentration of these radionuclides can be can show us that something can happen. Something happened, and for example, inert radioactive gases are parent. Xenon, for example, is parent for cesium-137, and that's why it is not correct to control cesium-137 in soils, because it is just a daughter radionuclide from xenon, from inert radioactive gas. And that's why it is important to control these gases. And of course, it is also should be controlled because of nuclear reactor operation. A small increasing of the dose of the concentration of noble gases under the reactor will show us that something incorrect in reactor, working incorrect. The contribution of noble gases in the total normalized discharge activity. Here you can see different reactors type, VR and RBMK, and you can see how many noble gases, carbon and tritium, are flowing outside because of normal operation of nuclear power plants with different reactors type. According to tritium, tritium can be natural and technogenic. Natural radionuclide tritium, and I want to say that all these radionuclides that should be controlled firstly, noble gases, tritium and carbon, there are all has two sources. They can be natural and can be technogenic. And it is another task to separate technogenic and natural radionuclides. For example, tritium. Natural tritium generating in the atmosphere, lithosphere, and ocean, and try into the atmosphere from outside. And tritium can be technogenic, and it come from nuclear and thermonuclear weapon tests, routine release and discharge from nuclear fuel cycle enterprises, and accidents and incidents and nuclear fuel cycle enterprises. But as you understand, the tritium is not very dangerous for people, but also it depends on concentration. Here you can see the tritium from different nuclear power plants in Russia. Nuclear power plant Beloyarsk. This is Mayak plant. It's enterprise that produce plutonium. And for example, Russian Federal Nuclear Center of NIF3. And here you can see that it is ongoing during the normal operating of all these enterprises. The green line is permitted level, and this line is actual level. And of course, all these interflows from nuclear power plants and nuclear enterprises, all these are really under the permitted level. The concentrations are under the permitted level, but it depends on permitted level. Nobody really knows what is the permitted level actual. What is the permitted level? Why it is here? Nowadays, most of scientists think that it is just should be a little bit upper than the normal operating contamination from nuclear enterprises. Here you can see, the median specific indicator of tritium discharge from European nuclear power plants. Also different types of reactors. Here you can see exactly which reactors, and gigabecquerels per gigawatt in different periods of time. And you can see a little trend for increasing tritium during the nuclear epoch. The total contribution of carbon and tritium to effective dose from various nuclear installations. Also different types of reactors. And you can see that contribution of carbon and tritium from the heavy water reactor achieve 99 and 99.99%. And you can see also that light water graphite reactor influence just 3.66% of tritium and carbon. It is very important for you to understand that different reactor types works different ways and contaminates environment in different ways. The median specific indicator of carbon-14 discharges from European nuclear power plants. Also different periods of time, different reactors types, and the significance of gigabecquerels per gigawatt per hour. Here the situation is a little bit better when with tritium, but you also should understand that from all reactors during the nuclear epoch, the carbon-14 is going outside and put some additional carbon to the environment. Conservative estimate of carbon-14 releases from various sources. This is a contribution of carbon-14 from nuclear power plants and natural activity of carbon, and carbon from nuclear weapon testing. You see that nuclear weapons testing and natural carbon are pretty high and are going together here. But the carbon from nuclear power plants is increasing year by year. And maybe in our life, we will see the crosses of these lines when carbon from nuclear power plants will be higher than the atmospheric carbon. Also with tritium releases from nuclear power plants, and here lines are more closer than to carbon. This is a nuclear weapon testing line. And here, natural activity of tritium in the atmosphere. And you can see that tritium from nuclear weapon testing affected more the environment than the natural tritium. And also we can see how fast the tritium releases from nuclear power plant increasing. And that's why it is very important to control the situation. Because you know that carbon, for example, is using as a marker for dating something. And it is very important to understand the total amount of carbon in the environment. Okay, maximum value of radionuclides concentration in Russian nuclear power plants airborne releases. And you can see here that the first radionuclides that's releasing every day, every hour from nuclear power plants is tritium and carbon, and after that noble gases. And you can see that strontium and cesium, also iodine and other radionuclides. And here you can see different nuclear power plants from Russia. As you understand, these radionuclides are going from parents' noble gases. And these numbers, I can repeat, is going every day and every hour in the normal operating of nuclear power plants. Another problem for monitoring, one problem is artificial radionuclides and controlling enterprises, and another problem is natural radionuclides. It is also a very important part of monitoring. For example, here you can see that comparison of cesium-137 to the old world ocean from various sources with the content of natural radionuclide, potassium, for example, 40, and uranium-238. And you can see that uranium and potassium makes more the most hard dose for the environment than, for example, Chernobyl, Fukushima, and global nuclear weapons testing. These radionuclides are very interesting for us because they are unique for the environment, and we can use them as a tracers for environmental investigation. And we doesn't really know how it affects to biota or to humanity. But these radionuclides are also important to control because the contamination is the existing of, for example, radionuclides in the environment in the not how to say, in the environment that have never been there, for example, for artificial, or in the amounts that have never been before. This is works for the natural radionuclides. And monitoring of natural radiation. This is the simple scheme, as well as that two artificial radionuclides, how it works. And you can see here all objects that should be controlled by environmental monitoring. And it is very important not only around the nuclear enterprises or nuclear power plants or others. It should work anywhere in every city. For example, in Europe, they made the digital atlas of natural radiation. And using this link, you can take a look. It is a very interesting atlas where they put the information about cosmic contribution and terrestrial contribution. And they estimate the radon risk index to the different parts of Europe. it looks like this. And this work is very important and one of the most important, I think, in the environmental monitoring all over the world for the closest years for our time. You can see here in that map, in interactive map, different layers with different radionuclides, with just those radon, uranium, and of course artificial radionuclides. And I think that it is our future. We should make this kind of map for the whole world to understand how radioactive affects to the humanity. This is just part of this atlas. I like this atlas because nobody, and as well as United States, didn't make something like this. The European Radiological Data Exchange Platform consists of data change mechanism and presentations of all radiological monitoring data. And of course, for example, if you want to choose the place for living, you should take a look for this map, maybe firstly. It's also good for people, for radiophiles and for radiophobes as well, yes, and for people who love the radiation and who doesn't. And to create these kind of maps, they used the following scheme. That environmental monitoring should contain, of course, natural conditions and the state of radiological knowledge of territory. And it should include the content of radionuclides and different environmental objects: air, soil, vegetation, fauna, local foodstuff, aquatic ecosystems, and others. And for state of radiological knowledge of territory should be based on equivalent gamma dose rate. And to estimate this equivalent gamma dose rate, we usually use individual thermoluminescent dosimetry. How it works. For example, this is Rupur nuclear power plant in Bangladesh. And before creating this station, it was estimated the local background. The food markets was used for the food investigation, the content of radionuclides in the food. And here you can see in the center should be the nuclear power plant, and this is 30-kilometer zone. Usually it looks like that people just buying products or food and measure it on gamma spectrometry. And individual dosimetry, how it works. You should choose some persons who are living on the territory you will investigate and give them the individual dosimetry for 1 year minimum. And better for 2 years or 3 years. And the people should live with these dosimeters and take it everywhere. And after that, you will estimate the dose. And of course, it should be only one person, it should be minimum 10 and better 100 of persons. This method is the best to understand the radioecological risk of the territory, because the individual dosimetry consists on all sources that can be affect to the person. And it includes air, soil, food, some equipment with that the person works, and others. Air monitoring includes different types of air, of course. It should be aerosol filters and planchets for the rain, for example, collection and snow collection. And atmospheric air sample points should be also in different zones from the nuclear power plant. but it also shouldn't be the very high amount of points. To estimate the situation, you can use only 8 points, 8 and 10 points. It will be enough. Of course, you should note the winds and the relief of the territory of investigation, but 8 points or 10 points will be enough for you. Soil monitoring usually separates soils for organic horizon and mineral horizons. It is enough for monitoring because radionuclides are usually consist on the upper organic soil horizon. And to estimate the situation, you just can measure this organic horizon and you will understand the background. Vegetation monitoring. Vegetation monitoring should include the plants that are growing and the most amount in the territory that you want to investigate. And of course, you should separate the grass to the different parts, or for example, you can measure the trees. Really, it doesn't matter because if you have background level, and all of us know that the coefficient of transfer from soil to grass is very small, less than 1% usually. And that's why it will be very unique if you find some activity in the grass and on the background territory. Fauna monitoring that I like very much. And usually also you should take samples from different parts of fauna, different faunas samples. But what is important here? When you analyze, for example, fish, you can only analyze this part, the back of fish, because only this part is important for human, because it's a part that we eat from the fish. And also for mammals, for cows and other domestic animals, it is firstly in monitoring, they measure only parts that can be eaten. And if the parts that can be eaten are clean, the monitoring is enough, it stops. Of course, for the scientific investigations, it is very interesting to analyze different parts of fish, different parts of mammals, and as well as phytoplankton, zooplankton, and others. And we, for example, here in radiochemistry division, we are making such experiments with different parts of fish or different parts of mouse and others. But for environmental monitoring, it is important to understand that we estimate the part that can be eatable by people. Water sampling. As an example for Upur nuclear power plant, I just want you to show that the monitoring points should locate it before and after the nuclear enterprise. Why it is important? Because if something happens on the nuclear enterprises, we can find the results here in the down part of the river after the nuclear enterprises. But if it is not enterprise and something happens, for example, here, we should be sure, that if we have some contamination here, we should be sure that is absolutely that it is a nuclear power plant accident and nothing else. And that's why for the water investigation, always, everywhere, it should be noted that the points should be before and after enterprise. How it works? Of course, firstly, you can estimate very fast. Water you can estimate very fast if you use a co-precipitation method. For example, you can use iron salts. It very often using a method for investigation water for radionuclides, of course, for radionuclides, because iron salts, for example, iron-3, can co-precipitate all radionuclides very, very well with very, very well yields. If we had for practice more time, firstly, it was the task when you first separate the cesium using this iron salts co-precipitation method, and after that separate strontium and yttrium. But we didn't have time. Maybe next school we will do it. But you also can see, and I recommend you to use this method to co-precipitate from 5 liters of water, 10 liters. And nowadays, when we are working with the background levels of radionuclides, we use 100 liters barrels. And we just put the iron salts and we collect all radionuclides from that 100 liter barrel water sample. Okay. Okay, this is the last slide. The further development of nuclear power industry related to ensuring its ecological safety. And it primarily requires the radioactive waste management problem to be solved, a reduction of the volume, development of new mineral-like matrix, and other studies. And reliable estimation of the effect of nuclear power plant, nuclear facilities plant on the environment requires new selective and efficient methods for pre-concentration of radionuclides to be created. So the summary is that nowadays also we have a lot of work for improving radioanalytical methods for radionuclides investigations. And for example, for nuclear power plants in Russia, we also usually measured noble gases, for example, and our equipment show us that it is less than minimum detectable activity. And this is another way we should create the equipment that can catch the small ultra low activities of radionuclides, because we know well that every nuclear enterprise influences radionuclides to the environment. Okay, thank you. Thank you very much.
Any questions?
Thank you, Doctor, for your presentation. I would like to hear a little bit more explanation on how we can use the iron salt for radionuclide measurement.
Okay, Vladimir.
Yeah.
Did you?
No, I will present.
You will?
Yeah.
You will have a special lecture about co-precipitation, about destructive methods of radionuclides analyzing. And it will be very interesting. Vladimir will present you, how it works. Yeah, I just showed you that how it works in real in the environment around the nuclear facilities, and what steps monitoring includes.
Okay. So, what is your personal opinion about the Fukushima tritium discharge?
Oh, of course, as all clever scientists, I think that it doesn't affect the environment higher than, for example, China nuclear power plants that disease tritium during the normal operation of nuclear power plants. And of course, the amount of tritium from Fukushima is less than La Hague tritium from France and England from Sellafield. But of course, we should control and monitoring situation around any diseases. And as I finish my lecture, we have a lot of work to improve the radioanalytical methods to find ultra low concentrations of radionuclides in the environment. It is very important because you understand that, for example, for Fukushima, when they disease the tritium, the dilution effect will work. And to find and control the situation, we need to improve radioanalytical methods.
Any more questions? If not, then thank you again.
Thank you.
So we will start the next lecture now, and after this, we will take a short break, okay? So. So I would start with the shorter one because you already have quite a lot of information about the classification of radioactive waste. Professor Ojovan showed you a lot of information about the classification of radioactive waste, about the norm waste, naturally occurring radioactive matter that are released or that are accumulated in different activities, not only during the mining of uranium ore, but also during operation with, I don't know, iron or with some phosphate minerals and or water purification and other. But I will just show you more examples about the sources of radioactive waste from the nuclear energy sources. That's why it will be not very long presentation, but short. Just few words about the nuclear energy production, because today we had a very nice presentation about the CO2 emissions and how it is important to reduce the greenhouse release. Just few words about the importance of nuclear energy in this field. There is diagram where you can see the production or emission of greenhouse gases from different sources of energy, and you can see that these four types of sources of energy, nuclear energy, wind and solar, and including hydropower, they are the lowest. They have a lowest impact in the emission of the greenhouse gases. Of course, the normal or conventional sources like coal, oil, and natural gas, of course, they produce quite a lot of CO2. But that is interesting that if we compare also death rate from the accidents and air pollution, including the accidents during mining, during the production of energy. You can see that these four types of four sources of energy, they will be the safest. Also, maybe you heard about the accidents recently in coal mines. So dozens of people hurt it, died. So every year, a lot of people so there are many accidents in coal minings, and I think you've heard about them quite a lot in the news. And there are not such a lot of accidents and disasters that are included these four sources of energy. So nuclear energy can be seen as a clean energy and one of the safest source of energy. There is nothing absolutely safe, so everybody should understand it. Even if you going just by car or if you're walking on the street, there is nothing safe at all. So everything, there is no 100% safety in any operations, in any actions, in any field of our life, including the production of energy. So we can only say that this can be more safe than this, by comparison one source with another. Also, I would like to stress a bit attention that nuclear energy is a very concentrated source of energy due to the very powerful nuclear forces that are responsible for production of energy. We can see that if we take just natural gas and just a normal vessel with natural gas with the volume of 26 cubic meter, the same amount of energy will be produced just by 26 milliliters of the nuclear fuel. So it is 1 million times difference in the volume, so in concentration of energy. That's why when we compare the area that that will be used for the production of the same amount of energy, we will see that the nuclear power plant will occupy much smaller area. Okay. Much smaller area, so it's also important nowadays. So altogether, these four types of energy, they form, let's say, this green square. It is, let's say, ideology of Rosatom. And we can see that these two most powerful sources of energy, nuclear power and hydropower, they serve like a base of this energy production, because they are stable. They have stable production of energy. It doesn't depend on I don't know, climate, on weather conditions, on whatever. But during the day, when we have a rise of the energy consumption, these two types of energy can serve as additional sources of energy. So altogether, they are very clean and the safest sources of energy. So once again, what is the radioactive waste? First of all, it is material that contains some radionuclides, of course, as it is radioactive. Also, what is waste? It is something that we don't have any use with the current technologies. It is one of the main points in this term, that currently there is no use, because in future it may be some new technologies that will be able to use these materials. But in the middle, there is something empty space, and it is also important because we call radioactive waste materials that contains radionuclides, but at concentrations or activities greater than the clearance levels that are established by the government. Yeah, and these materials have no further use with current technologies. And Michael Ojovan told you quite a lot about these levels. And I also would like to stress your attention that all these clearance levels, IAEA, this International Agency on Atomic Energy, can recommend some levels, some schemes, some models for classification of radioactive waste. But any country is responsible to make their own decision on these levels. So IAEA can just recommend, make some support, some I don't know, expertise of the documents, but it cannot say that you must take these levels. Any country should decide by its own. And if we are looking on the nuclear fuel cycle, it's not only the production of the electricity at nuclear power plant, but it started with uranium mining, conversion, extraction of uranium, conversion it to uranium hexafluoride for uranium enrichment, then fabrication of nuclear fuel, then nuclear fuel goes to the nuclear power plant, produce electricity, and after some period of time, spent nuclear fuel goes to the near station pool for cooling, for storage for some years. And then there are two ways. Again, it depends on the country. It can be open nuclear fuel cycle, when the spent nuclear fuel goes directly to the disposal of spent nuclear fuel, or it goes for the reprocessing, where we extract uranium and plutonium and produce the fresh nuclear fuel that goes again to the nuclear power plant. So it is closed nuclear fuel cycle. And if we look at each step, we just go briefly through each step, starting from mining of uranium that can be in different ways. Either it is carriers or mines or underground leaching. Almost in all these cases, we will produce tailings. And these tailings, they contain naturally occurring radionuclides, but concentrated due to the actions of sulfuric acid, due to actions other reagents. And these tailings, they possess quite high hazard, radiation hazard for population, because in these tailings radium is concentrated, and radium is a source of the radioactive gas radon that is quite dangerous, because it is inert gas, it goes everywhere, and it goes to the people's lungs and irradiate it. And according to the World Health Organization, radon is the first reason for lung cancer for people who don't smoke. Of course, for people who smoke, the first reason for lung cancer is smoking. But yeah, radon is the second reason. So it is really a big problem. Hopefully, nowadays, in many countries where these tailings are existed, government make a lot of efforts to rehabilitate these territories, to remove these tailings, or to cover them with the special linings, waterproofs, etc. Then from the mining, we go to extraction of uranium, and then to conversion of uranium hexafluoride. And here the main waste, they contain, of course, mainly uranium, so it's not very radioactive, but they contains fluoride. So, and fluoride is toxic just by its chemical properties. The hexafluoride is very good material, uranium hexafluoride, because it has very low sublimation point, temperature point, only 56 centigrade. So it's very easy to evaporate it and then to use in the enrichment facilities. It can be either diffusion method, where we use membranes to separate light and heavy molecules, or nowadays in Russia it is mainly gas centrifuges that use the difference in the masses in centrifugal field, so the heavy mass go to the walls of the cylinder, and the lighter molecules stands in the middle of the cylinder, and we can separate these flows. So these facilities, there is almost nothing with the chemical reactions. It's mainly physical separation of the isotopes, but the facilities, they're quite huge, and of course uranium hexafluoride is very volatile material, can go outside, and the soils around such facilities contains quite a lot of uranium inside. Then we go to the fuel fabrication. We convert our uranium hexafluoride to the mainly uranium dioxide. It is the main component of the nuclear fuel nowadays, but I should mention that this year the first reactor in Russia with fast neutron spectrum was completely equipped with the mixed oxide fuel containing uranium and plutonium. So it was the first time in the history of nuclear energy then the reactor was fully equipped with this type of fuel. But again, the most popular type of fuel nowadays is just uranium dioxide. These pellets of uranium dioxide, they put it in these elements that are then assembled in the fuel assembly, and they goes to the reactor. Again, there is almost nothing with chemical reaction except the conversion of uranium hexafluoride to uranium dioxide. But when people checked the quality of the fuel, they can say that this fuel is not suitable for production of the fuel assembly, and thus this fuel with defects, old fuel, they are dissolved. These fuel pellets, they are dissolved and purified and refabricated in the new pellets. But during this operation, we produce quite a lot of liquid radioactive waste. Then fuel finally assembled in fuel assemblies go to the nuclear reactor. We produce electricity, and it seems that everything is okay, but actually the water that is going in nuclear power plant contains some radionuclides, and it must be purified, and the purification is made with the resins, just ion exchange resins, and this ion exchange, of course, containing radionuclide become radioactive waste, and very problematic radioactive waste. And then the spent nuclear itself, if initially, again, it was just two elements, uranium and oxygen, but after the work in the nuclear reactor, now we have more than 50 different elements, and most of them are not suitable to work in nuclear reactor. So we have 50 elements, but they are only 3% of mass of the spent nuclear fuel. So we can, the idea is to remove this 3% and to extract remaining uranium and accumulated plutonium to make the fresh nuclear fuel. So this 3% of the radioactive waste just remove and take the 97% of the reusable material. So very nice idea. So that means that the spent nuclear fuel is not always radioactive waste. In Russia, it is not radioactive waste, and we can use it in closed nuclear fuel cycle. But it is not the only reason, not only to use uranium and plutonium and again, but also with the reprocessing of spent nuclear fuel cycle, we can reduce the long-term hazard of this material. Actually, spent nuclear fuel is, I would say, the most dangerous or hazardous material on our planet. And it stays very dangerous for a very long period of time, let's say 100,000 years. But it is so because long-lived radionuclides like plutonium, americium, neptunium are inside this spent nuclear fuel. If we remove them, then we can decrease this hazard of the material down to 300 years. So it is very good decrease of the hazard of the material. So not only reuse the material, but also to decrease the toxicity of this material, long-term hazard of this material. And the extracted long-lived radionuclides we can burn down in the new types of the nuclear reactors, reactors with the fast neutron spectrum, that actually work today, BN reactors with the heat carrier sodium. And now the new types of the reactor is under construction already in Tomsk region in Russia. It is not industrial reactor. It is, let's say, semi-industrial reactor because the power generation will be 300 megawatt. So it's not a normal industrial reactor, but it is a model for the development of the industrial reactors with the capacity of 1,200 megawatt. So again, we can burn this long-lived radionuclide in such reactors and thus decrease the long-term radiotoxicity of the materials. And it will allow us also to decrease the volume of the high-level radioactive waste from this volume to this very small stone in the ring on the finger. But of course, when we reprocess spent nuclear fuel, we dissolve it, we extract components, we produce quite a huge amount of the liquid radioactive waste. And unfortunately, in the past, liquid radioactive waste, they were just dumped either in open reservoirs, in rivers, in lakes, or they stored in the cement or tanks with some stainless steel, but these tanks, they are already expired, and there are some leakages of these tanks, so there are quite a lot of problem today. So that's why the new reprocessing plants for reprocessing of spent nuclear fuel, one of the main requirements for these plants is to exclude the release of liquid radioactive waste because they are quite dangerous. And of course, as you already heard today from the first lecture, we need, when we store or when we dispose radioactive waste, we should think about the multi-barrier concept, about different barriers starting from the matrix with radioactive waste should be stable, durable, mechanically stable. Then there is the package itself and some buffer materials that should prevent the release of radionuclide in the environment. But just a small point about the radioactive waste that as far as they are radioactive, that means that they are decaying. And they decay with time with exponential law. That means that the hazard of spent nuclear fuel will decrease with time, and sooner or later it will reach the hazard of just natural uranium ore. That means that the same activity that we take from Earth, we put back to the Earth. It's like in Russia we called it a radio equivalent, so radioactivity equivalent. And it is not the case for, let's say, conventional contaminants like mercury or other heavy metals that are not decaying. They will stable for eternity, and they will possess hazard for the whole time when our planet will exist. But these materials, spent nuclear fuel and radioactive waste, they have a finite hazard. So going back to what are the sources of radioactive waste, I would say that any our operations with radioactive material will generate radioactive waste, and our task is to make the storages of radioactive waste safer and to reduce the volume of radioactive waste. There are other non-nuclear fuel cycle facilities that generate radioactive waste. First of all, medical procedures with the radiopharmaceuticals or with the sources of ionizing radiation like cobalt-60 or cesium-137. It is industrial sources of ionizing radiation that are used for defectoscopy. So you can see this indium sources for X-ray analysis of the defects in the materials. Of course, there are waste from the research institutes, research reactors, other research facilities. You've already heard about the norm waste that are produced from just processing of normal ores, and also the food and agriculture facilities that used sealed sources of ionizing radiation to make the to sterilize the seeds and food. These sealed sources finally become also radioactive waste. So quite a plenty. But of course, the main source is still nuclear fuel cycle facilities. So brief conclusions that nuclear energy, of course, important and green source of energy. But it is important to remember that nuclear energy, it is not only the nuclear power plant, but it is all stages of nuclear fuel cycle, starting from uranium mining to the final disposal of radioactive waste. And radioactive waste, they are the results of any activity with radioactive materials. But with modern technologies, with the developing technologies, we are trying to reduce the activity and the volume of the radioactive waste to reduce the long-term hazard for our next generations. Yeah, and we of course should remember about the multi-barrier system when we are talking about the storages or disposals of radioactive waste. So thank you for your attention. Now we have a short break, and we will continue with the analysis of environmental samples. Thank you. So, guys, let's start. So, and talking about the analysis of radionuclides, the determination in environmental samples, we will start just with maybe a reminder or maybe new information about the detection of ionizing radiation, just some basic information. First of all, we should remember that we cannot see or feel ionizing radiation by our organs. That's why we can analyze the presence of ionizing radiation and its quantity only by interaction of radiation with matter. And there are different mechanisms of interaction. Main of them are ionization and excitation. In this case, we detect the electric current in our detector system, and that's why detectors are called ionizing detectors. Excitation means that we excite the electronic levels in molecules, and we can detect the visible light that is emitted due to the relaxation of this excited electronic system. And in this case, we use scintillating detectors. There are two other mechanisms. It is production of defects, and it is mainly track detectors that we use to analyze these defects, or it is absorption of the energy of the radiation and the measurement of the heat with the colorimetric detectors. So, but we will speak mainly about these three main mechanisms. And what is important for choosing detectors, it is characteristics of the detectors, and one of them is efficiency, of course. That means how sensitive our detector to a specific type of ionizing radiation, alpha, beta, gamma, or neutrons, if we need one. And the resolution. And resolution can be time resolution or energetic resolution or spatial resolution, depends on the detector that we are using. And in principle, resolution is the ability to distinguish between two events, either in time, if we have two particles that are going one after another, and if our detector has very bad time resolution, then we cannot distinguish with these two particles, and we will count only one of them, so we will lose in the efficiency, and other we will see. So we will start with the liquid scintillation counting that you used in practical work. And principal scheme of this method that we have liquid cocktail, organic cocktail. The diluents normally aromatic hydrocarbons, and some scintillator molecules. They're different in different cocktails, but the idea is the same, that the ionizing radiation goes from radionuclide to our cocktail. And firstly, it meets the solvent molecules, because there are much larger amount of the molecules of the solvent. There are only 2 to 3% scintillator molecules, so just probability to meet solvent molecules is higher. That's why the energy goes first to solvent molecules, and only after this goes to the scintillator molecules that emit light that is further detected by photomultiplier tube. We use different types of vials. These plastic vials are more popular in our investigations. The glass vials also can be used, and this special vial that converts gamma radiation to the visible light. these are typical spectra of beta radiation that we detect with scintillation spectrometers. And you can see in case of strontium, we can see two peaks. But we cannot really distinguish good between these two peaks because any peak has this very long tail. It is even distribution of the energy. So it's not very easy to deconvolute the spectra. It is possible, but it is not 100% correct. But the problem with liquid scintillation that we can have a quenching effect. What does it mean? It means that in our system there can be presence of some chemicals, some additives that can take the energy from the solvent molecules and prevent this energy transfer from the solvent molecules to the scintillator molecules. So this energy goes not to the scintillator molecules, but to this chemical additives that quench also our scintillations. So that means that there is no light that will go from the scintillator molecules. We lose our photons. It is quenching effect. Another types of quenching, it is color quenching or physical quenching. In this case, the scintillator molecule get the energy from the solvent molecules. It emits light. Everything is going well, but we have some color impurities that absorb the emitted light. So again, we lose our photon to the color agent. Again, less photons will be detected by our system. What does it mean? It means for the detecting systems that if we have less photons, the energy of particles is lower, and we observe the shift of the peak of our radionuclide to the lower energies to the left. And also in some cases we can lose all photons. That means that we lose also efficiency, so we detect less events than it should be. So it is important mainly for low level beta emitters like tritium, carbon-14 or nickel-63 or other radionuclides. You can see that the efficiency of detection depends on this quenching parameter, and this dependence is very important for tritium that has the lowest energy of beta particles. So the efficiency of detection, even with this highly efficient detection system, is around 60% for good samples for tritium. So again, quenching is very important, and we have to check this quenching parameter when we are using liquid scintillation spectrometers. But what is interesting and what is very useful, that the pulse from the irradiation. So when particle goes to our liquid scintillating system, all photons they emitted not at once. It is quite prolonged process, not very long process. It's something like nanoseconds, so 10 to minus 9, 10 to minus 8 seconds. So for us it's very short, but it has some durations, and this duration depends on the initial source of the radiation. If it is beta particles, this pulse is shorter than for alpha particles. So we can say that in case of alpha particles, our system irradiate lights for longer period of time. So if we have electronic system that allows us to analyze this shape of the signal, and also if we have a terminator of the pulse, we can say that okay, before this time, during this period of time, we detect together alpha and beta particles, so the signal from alpha and beta particles. But after this time, we detect only a signal from alpha particles. That means that we can separate our spectrum onto alpha, only alpha containing particle, and alpha and beta containing particle. But if we know the amount of alpha particle, we can subtract from this summarized spectrum alpha and beta. So if we know how many alpha particles we have, so we just subtract it, and now we have only beta particles. So we can see clearly alpha and beta spectra separated, even if we have alpha and beta emitters in one sample. So it is very powerful technique to distinguish between alpha and beta emitters that are present at the same system. Another good parameter or good characteristic of beta particles that they can move faster in media than the light. We know that the speed of light cannot be higher in vacuum, but in media we can move faster than light. And for electrons, or for beta particles that are electrons, this threshold is around 260 kiloelectron volts, and there are some radionuclide that can that emits beta particles with this high energy. If particle goes faster than the speed in the media, we can observe this production of the Cherenkov radiation, Cherenkov light emission, and in this case, all media emits light in this blue-violet region. And there are some important for us radionuclides. It is not the full list, just some examples of radionuclide that have energy of beta particles higher than 260 kiloelectron volts. And you can see that for yttrium, for good spectrometers, we can reach efficiency up to 70%. If I remember, Natalia Kuzmenkova told you that for our spectrometers, efficiency was around 50% for yttrium by counting the Cherenkov. What is good for Cherenkov counting, that we don't need to use any scintillator. Yeah, so we just need water that irradiates, that emits light, nothing else. No organic cocktails, no organic liquids. Very good and very cheap for us. Normally, in liquid scintillator spectrometers, we have two photomultiplier tubes, because each of the photomultiplier tube creates quite a lot of noise. So due to the thermal fluctuations, photomultiplier tubes can give parasitic noise. And to avoid this noise, we use two photomultiplier tubes. They are connected to such called coincidence mode, coincidence scheme, when only those pulses, those events that goes immediately or together from two photomultiplier tubes, they will be analyzed. So they will be fixed. If the signal will go only from one photomultiplier tubes, it will be ignored. So because it is this parasitic signal. So, and this coincidence scheme help us to reduce the background signal. And there are typical equipment for liquid scintillating counting. It is Perkin-Elmer company, USA, that now has this Quantulus trademark as well, and the Hydex company. And so it was about liquid scintillator counting, and now about the alpha spectrometry. With alpha spectrometry, we normally use semiconductor detectors with the silicon detector, silicon material. For us, silicon is quite good if we are talking about the alpha spectrometry, because normally the energy of the alpha particles, they are in the range from 4 to 5 mega electron volts, or even higher, 6, 7 mega electron volts. And the resolution of the silicon detectors is around 30 kilo electron volts. So it is not very good for gamma spectrometry, but for alpha spectrometry, it is high enough. So it is around less than 1% in resolution. So you can see that with these detectors, we can detect very nice sharp peaks of alpha particles. But as far as alpha particles, they interact with matter quite intensive, even with air. The pressure in this vacuum camera is important to be controlled, because depending on the remaining pressure in our camera, you can observe the shift in the energy of alpha particles. So if you, for example, calibrated your spectrometer for the energy of 20 millibars for this pressure of air, so you said that in your channel, let's say 1200, the energy of particle is around 5.5 mega electron volts. But the same peak, the same energy, but at different pressure, will shift it to another channels, so you can ignore it, or you can misinterpret your data if you calibrate it at different pressures. So it is important to remember. Also, another important point that for alpha spectrometry, we have to prepare a very nice spin sample by using either electrodeposition or microprecipitation, because if you have fixed sample, let's say, then part of the energy of alpha particles will be accumulated, will be lost in this sample itself. And as far as we will lose energy of alpha particles, we will see not the sharp peak, only with one value of the energy, but we will observe this very bad tailings of our peak. And just imagine if you have several peaks and each of them have this tailing, then you will have very bad spectra, and it will be difficult to analyze, not only to identify the radionuclide, but also to analyze the quantity of this radionuclide. So for electrodeposition, normally we use such system where you have a metallic disc, maybe it's stainless steel or nickel disc or other material that is connected to the negative electrode, and you have this platinum wire, platinum anode wire, positively charged. So, and in this system, you put your solution with the radionuclide connected to some voltage, and you have the deposition of the radionuclide in this stainless steel disc, very thin, good layer. Or you can use these filters. They are already contain some cerium fluoride or barium sulfide, and during the filtration of the solution through this disc, through this filter, you have a co-precipitation of your radionuclide on this already prepared nice layer. So you can use both of these methods. This is cheaper, this is more convenient. So depends on the laboratory where you work. And there is an example how different methods can give you different information about the same system. So it is radium-226 that is measured with liquid scintillation counter. You see this not very nice, honestly very bad resolution of the peaks, and the same sample that was prepared and measured for alpha spectrometry with very nice sharp peaks and a lot of information. So typical examples of alpha spectrometers. Let's go to them. So, and if we would like to find some particles that accumulated our radioactive matter, our radionuclide, we can use the track detectors, either plastic detectors, where we analyze after etching of the defects, or today we can use this nice computer radiography, when you can use more or less the same phosphor screen or phosphor imaging plate several times. So these plastic discs, they can be used only one time. So because they are defected, you cannot use it anymore. But this in these systems, they can be used many times. So they very easy to use. So gamma spectrometry. For gamma spectrometry, we have a lot of different processes when gamma quantum interacts with the material of the detector. What we would like always to detect, it is so-called photo effect, when the whole energy of gamma quanta accumulated, absorbed by the electron, and this electron creates ion pairs in the detectors, and we absorb the whole energy of gamma quanta, so we have this nice peak, very sharp, and by the energy of this peak, by the position of this peak, we can identify the radionuclide, and by the area of this peak, we can say what the amount of the radionuclide. But unfortunately, we have many other effects like Compton scattering. That means that part of the energy of gamma quanta will be scattered and can go outside of the detector, and thus we will detect not the full energy of the gamma quanta, but some distribution of the energies. So we call it Compton continuum, because it is continuous spectra of the scattered Compton gamma quantum. Also, if we have gamma quanta with the energy higher than 1022 kiloelectron volts, we can generate positrons, electron-positron pairs inside the detectors. And this positron will annihilate with the electron and create two gamma quanta. If this two gamma quanta absorbed in the material of the detector, then we don't lose any energy, and we again detect our peak. Everything is good. But if one or two gamma quanta will escape the material of the detector, then we will observe two more peaks with the energy less than 511 kiloelectron volts or 1022 kiloelectron volts. And this is one of the example of the real spectrum of yttrium-88. This peak is related to yttrium-88, and these two peaks, the first one is the peak of single escape, and in this peak of double escape of this annihilated annihilation gamma quanta. So why it is important? Because if we don't know that it can be the escape peak, we can try to find any radionuclide with the same energy, and I'm quite sure that we can find something with the energy very close to this value, but it will be not realistic because there is no such radionuclide in our system. It is just this additional peak from this peak. So interpretation of gamma spectrum sometimes can be very difficult. Also, for if we have several gamma quanta that goes from the one radionuclide, and if the activity of this radionuclide is quite high, then we can observe the summing of these energies, and we can observe the total, the peak with the total energy of these two peaks. Again, there is no radionuclide with this energy, it's just the consequence of the summarizing of these two. So again, it is important to understand what you measure. Different detectors, even if they are made from the same material, it is important how they are made, what is the technology of their production, what the geometry sizes of these detectors. And typical coaxial detectors, they're used in, let's say, any radioanalytical lab, but they have very low energy, very low efficiency for gamma quanta in a low energy region. It doesn't mean that they are bad, it just means that they cannot be used in this region. If you need to measure gamma quanta or X-rays in this region, you just need to use another detector. So it depends again on your task. Also, for example, just imagine if you measure only one radionuclide, like for example, cesium-137 in typical radioanalytical lab. You don't need to analyze the full spectrum of the gamma quanta. Then, in this case, you don't need really a good resolution because you have only one peak. It will be always in one position, and it doesn't matter if it is very broad or very sharp. You have one peak. But if you have unknown sample and you have to identify different radionuclides in this sample, then you must have very good detector with high resolution. Otherwise, you cannot distinguish the energy of different gamma quanta, and you cannot identify the radionuclide. For beta emitters, one of the important mechanisms of interaction with matter is so-called Bremsstrahlung, or stopping radiation in Russian language. So that means that if you have the flux of the beta particles or of electrons, and if you have any material that can decelerate or can stop electrons, you will produce the X-ray from this material, because it is physical law. If you have charged particle and it goes with the acceleration, it will generate electromagnetic wave. So if you stop charged particles like beta particles, you will generate the stopping radiation, or from German Bremsstrahlung. And if we look this spectrum of this radiation on liquid scintillation, you see this quite broad spectrum depending on the particles that are interact with matter. But also, as far as this radiation, it is X-ray, we will detect it with our gamma spectrometers. So how to avoid the effect of the presence of beta emitting particle, beta emitters in your sample when you measure gamma spectrum? It is quite easy. You just need to have some filter to avoid soft X-ray. For example, you can use aluminum with thickness, let's say 1.5 or 3, or depending on activity of your sample, maybe a bit thicker aluminum disc or aluminum filter. So aluminum is light element. It is efficiently stop beta particles, and the intensity of the stopping radiation of Bremsstrahlung will be quite low. So aluminum will help to avoid the formation of the stopping radiation in your spectrum. So it is initial spectrum of some radioactive waste, and this is spectrum with the aluminum filter. So you can see that this noise is decreasing with the use of aluminum signal. So it was about some basic principle of the detection. For alpha and beta particles, we can use, for example, liquid scintillation counter, or for alpha emitters, we can specifically use alpha spectrometry, or for if we have gamma emitting radionuclides, we can use gamma spectrometry. But for almost all of these methods, especially for liquid scintillation counting and for alpha spectrometry, we have to prepare our sample for this measurement. We have to separate radionuclides to avoid the interaction of or effects of the different radionuclides on our spectrum. To do this, we normally perform several stages in our analysis. First of all, it is homogenization of our material, adding some tracer to check the chemical yield of all of our process. We pretreat our samples, either we pre-concentrate if it is liquid sample with, for example, iron co-precipitation, or we dissolve or leach if the samples are solid. After this pretreatment, when we finally have the solution for work, then we separate our radionuclides with different methods. And only after separation of radionuclides, we prepare the counting source and perform the measurement. The destruction of sample can be done with different methods, depending on what sample we are analyzing. It can be soil or sand or even concrete materials from some building materials, or it can be metallic parts of, I don't know, of something. So for different materials, we can use different methods for its dissolution or for its destruction. One of the very efficient way is fusion. So you add some special reagents that help to melt your sample. And after melting, it dissolves, it becomes homogeneous. After melting, you can easily dissolve it in water. And again, for different materials, so you will have presentation, and if you will need any comments, you can ask. But if you can easily see from this table, if you have, for example, soil or metallic components or what other components, from this table, you can choose which flux, so this reagent, you have to use to dissolve your material. So very easy and very efficient. So you completely dissolve your system. If you have, but this works very good for small samples. Yeah, you can see the size of these vessels are not very big. It may be few grams of your sample, but if you have very low active sample, you need, let's say, 10 or more grams. And for this, you can use microwave digestions. So it is heating of your sample with acids, but heating with microwaves. It is very fast. It is very homogeneous again, heating without any losing of your solution. And so it is really convenient to use. So, and again, for different materials, you can use specific types of the digestion agent, acid mainly, or in some cases, it is addition of peroxide or other components. So for different components, you can use it. What is important, not forget to add some tracer, because if you perform so many chemical stages for preparation of your counting source, you can, of course, lose something. And to understand how much did you lose, you need to put some indicator in your system. So, in principle, we can divide all traces onto 3 groups. It is isotopic carrier, so it is the same element, but the stable isotope of this element. For example, if we would like to analyze strontium 90, we can just add stable strontium as a carrier. But it's not a tracer. So it's some mistake. Yeah, sorry. For tracers. Okay. Now it's not tracers, it's carriers. Carriers will be important for us because we will see from the precipitation procedure that it is not always possible to make a precipitate with our radionuclide, because the concentration of radionuclide can be such low that there is no formation of precipitate can be achieved. So to make it possible to create a precipitation, we add some carrier, some macro component that gives us precipitation. And in this case, yeah, we can use isotopic carrier. Again, it is stable isotope of the same element. For strontium 90, it can be just a normal strontium, or for, I don't know, iodine 129, we can use just a stable iodine. It can be non-isotopic carrier, but specific non-isotopic carrier. For example, if we would like to, again, analyze strontium 90, we can add, for example, not strontium, but calcium. Yeah. Or if we would like to analyze radium that don't have any stable isotopes, we can add some barium or calcium or other elements for its precipitation. And in some cases, we can use non-isotopic, non-specific carrier. For example, we can use iron to co-precipitate actinides. So it's absolutely different chemical properties, but actinides will be efficiently co-precipitate with iron. So, and with knowing the activity of added carrier, we can, after analyzing the spectrum of our sample, say what is the chemical yield of the whole our procedure. For separation of radionuclides, we can use different methods, but all of these methods contain the border between two phases. And this border can be between liquid and solid, so it is precipitation and chromatography. It is border between liquid and liquid, it is extraction, or gas and solid, gas adsorption, or sublimation of some components. And we will start with the precipitation again. To create precipitate, we have to reach some specific conditions. Any insoluble components has some finite solubility. So there is nothing insoluble at all. There is just a limited solubility of some components. And we can see the solubility product constant in database. So there are plenty of the data about solubility product of different materials, of different compounds. And if we have concentrations that together gives the product higher than a solubility product, then we will have precipitate. If the product is less than solubility product, then it is no precipitate. And again, yeah, these carriers, we already talked about it. And there are some examples of the carriers that can be used for separation of specific radionuclide. Here it is even more examples. Again, if you have some specific task, like, for example, analysis of concentration of technetium in environmental samples, then you can use some special carriers to do this, to make this analysis. And again, these special filters for alpha spectrometry, they use these layers of cerium fluoride or barium sulfide because they efficiently co-precipitate different components, actinides, radium, and other radionuclides. So precipitations can be very selective. We can precipitate only one element or one group of elements. It is very simple. So it is, I would say, the basic operation in chemical lab, and it can be easy scaled up from milligrams to industrial, I don't know, kilos or even higher, larger amounts. But precipitation is time consuming. You have to precipitate, you have to coagulate this precipitation, wait some time, then filtrate, etc., etc. You need to add some carriers. So again, it is consumption of reagents. Actually, it is not very technological. So the separation of the precipitate from the solution is not very easy sometimes. And yeah, precipitate finally will be contaminated. So what is more, what we use more in practice, it is solvent or liquid-liquid extraction. So it is mixture of two immiscible liquids. Normally it's water, aqueous solution, and some organic polar or non-polar solution. And water can be a heavy phase or it can be a light phase, depending on your system. But what we are doing again, we have some feed aqueous solution, some contact with organic phase. After the extraction, we have aqueous phase called raffinate, yeah, some remaining here, and extract contains our main component. And then if we need to convert our components back to aqueous phase, we use back extraction with water or other specific aqueous solution. So solvent extraction nowadays really quite fast and very selective, because for any radionuclide we can choose some specific organic ligand that will take only this radionuclide from our aqueous solution. It is very technological. Solvent extraction used in many technological process, starting from hydrometallurgy to biochemical production, etc., etc. But of course, there are some cons. First of all, it is use of toxic and flammable solvents. Sometimes efficiency and selectivity is not high enough, so we have to make multiple extractions. And of course, if we are talking about the processing of radioactive waste or radioactive materials, we produce quite large volumes of organic waste that are really difficult to process further. And chromatography. Now, chromatography is very efficient way, very selective way to separate two components, because yeah, I will show this slide. Because if in extraction we have only one contact between two phases, in chromatography it is multiple contact of the phases during the movement of the mobile phase towards the inert phase or stable phase. So we can say that it is multiple times repeated process of the redistribution of components between two phases. So we perform not only one contact again, but many contacts, and thus it increases the efficiency of the separation of the components. Today, normally we use resins, so it is some organic polymers, normally some vinyl copolymers with different other organic components. And why they're widely used? Because these aromatic rings can be easily modified with different functional groups, either with some groups with negative charge, like carboxylate group or sulfonate groups, or they can be modified with the positively charged components like amine groups or pyridine groups or imidazoline groups or other groups. So, and these resins, depending on the functional groups, can be used either for cation exchange, so that means we can exchange our protons in these groups with other cations like radium or actinides or whatever, or we can use them as anionic exchangers. That means that we can exchange this, for example, fluoride with pertechnetate or with anionic complexes of different metals. For quantitative determination of the properties of our resins, we can use distribution coefficients, the separation factors, etc. Let's go further. And what are the good benefits of ion exchange? It is really simple and efficient method. Simple because you have just a column, you put some solution, you take solution from the column, very easy to use. And you have a really wide range of applications. For example, any of dish washing machine, or I don't know, just a washing machine, they have the resins inside for to control the amounts of metal cations in water, etc. So you have resins everywhere. So they're really applicable for many applications. You can easily recover these materials, and yeah, you can use it for very efficient separation of different ions. But what are problems with the ion exchange? So for separation factors, even I told you that they're efficient for separation, but if we compare the separation factors for elements with close chemical properties, the separation factors will be not so good. And what the main problem, especially at nuclear power plants, that they generate quite a lot of problematic secondary waste. And the development of this chromatography technique is so-called extraction chromatography. In this case, we use the efficiency of chromatography because it is dynamic process, so it is multiple contact of two phases, but with low selectivity. We take extractants that I mentioned, that we can use specific organic ligands for some certain radionuclide to improve the selectivity, and mixing these properties together, we obtain this so-called extraction chromatography. Extraction chromatography, as far as we use extractants here, all the benefits, let's say, of extraction is going to extraction chromatography. How it actually looks? We have some porous media, some porous polymers that are saturated with the organic phase containing our extractant. Then diluent is evaporated. So finally, in our pores, we have so our pores are saturated with the extractant. So again, we have the same resins, so this is the same granules that we put in column, but each of these spheres, they are covered with the specific extractant. We can use some specific cartridges that looks like this. So we put just solution in this cartridge, and it goes through the sorbent, through the extraction resin, and our radionuclide of our interest is absorbed in this resin, and other goes through the column without absorption. And this box, vacuum box, can be used to facilitate the flow of the solution through the column. And again, for different applications, there are already many of the commercially available resins. If you need to separate actinides or technetium or strontium or whatever from the natural samples, you can take this table and look on the resin that you need to use. There is no secret about the composition of this resins. The main not secret, but the technological problem is to create even distribution of extractant on these granules, on this polymer base. Some examples of these resins, for example, actinide resin that is used for separation of different actinide. When you will look for specific resin, you will also always find in the catalog the dependence of the distribution coefficient of elements of your interest on this resin, and depending on what you would like to separate, depending on the conditions, so you can adopt your your method to separate specific element. So the higher the value, the higher bonding of your radionuclide on this resin. Just another example of TEVA resin. So it is a specific resin for tetravalent actinide. So we can see, for example, neptunium pentavalent is normally not sorbed, or at some concentrations of nitric or hydrochloric acid, technetium no more sorbed on this resin. But for example, thorium-4, neptunium-4, and plutonium-4 has quite high distribution coefficient. So at nitric acid with concentration higher than, let's say, 3 mol per liter, you can easily separate only tetravalent actinides without any influence of other radionuclides. So very efficient again and very easy to use. UTEVA resin is sensitive for tetravalent and hexavalent actinides. So it's 4 and 4, but it should be 4 and 6 valent actinides. So it is used to separate plutonium that is mainly in form of tetravalent plutonium, thorium that is always in tetravalent form, and uranium that is normally in hexavalent form. So again, from all the others elements like trivalent americium, curium, and other components can be easily separated. Another important for us example is strontium resin. To extract strontium or to sorb strontium, in this resin used so-called crown ether. In this case, it is 18 crown 6 ether, and it is known that different crown ethers, depending on the size of this cavity, they are sensitive to different alkaline and alkaline earth metals. And you can see that this strontium resin in the nitric acid media in these concentrations is very selective for strontium in the presence of alkaline metals, and also it is very selective even in the presence of calcium or radium. It is not very good separation from barium, but at a very high concentration, like 10 mol per liter of nitric acid, you can separate even strontium and barium as well. So extraction chromatography, it is highly selective method for production. Again, as any chromatography method, it can be used in so it has high productivity. And as far as it is very selective method, it can be used for separation of individual radionuclide. But there are also disadvantages. First of all, maybe not first, but it is quite expensive materials. But also these resins, they are bleeding. That means that as far as we just put some extractants on the surface, let's say, of polymer, it doesn't covalently bound to the polymer. So with few operations, our extractants can go from the polymer. So we lose our extractant from the polymer base. So it cannot be used many times, maybe 2-3 times, not more. And as any chromatographic resin, we have a limited capacity. So in summary, the separation is needed if we would like to use detection methods such as liquid scintillation counting or alpha spectrometry. And we have to use these methods when we are talking about difficult to measure radionuclide, like pure beta emitters or pure alpha emitters. They cannot be analyzed with other techniques. So there are a variety of methods to separate radionuclides, starting with precipitation, ion exchange, solvent extraction, and state-of-the-art extraction chromatography. But to control the chemical yield, we have not to forget to add some traces. To improve the chemical recovery, we can use different carriers. So I think that is all for this lecture, and I propose that we finish for today, if you don't have any questions. No questions? Okay.